Good evening, friends. Welcome to day 6 of the Six Sigma Masterclass Elite sessions. So, yesterday we looked at measurement system analysis, which is an important section in measure phase. And this is a very, very important exercise that we need to perform on a routine basis, not just at the time of working on a Six Sigma project, because we need to validate the correctness of the base data that we would have collated for the CTQ metric through this exercise, right? And we also looked at how to perform this exercise both for discrete as well as for continuous data scenarios. And then towards the end of the session yesterday, we got introduced to probability distributions. So we will continue with our discussions regarding probability distributions. Let me share my screen. So what is probability? As we discussed yesterday, probability is nothing but chances of occurrence of an event, and distribution is the signature of a data set. So in our probability distribution exercises, so we'll be looking at the data distribution, and we will also have the historical performance of a key metric, and based on which we would be estimating the probability of occurrence of certain number of events. So yesterday we looked at few examples wherein kind of estimated probability by chance, right? So whenever we estimate probability by chance, when there are only two options for a result, the probability of occurrence of a particular option will be 50-50%, right? And if you have three options as a result, then the probability of picking up an option will be 33.33%. And when we have four options for a result, the probability of picking a particular option would be 25%, right? So as the number of options increases, the probability of picking a particular option would actually reduce. So this is what we would call as probability by chance. And as I told you yesterday, so we will have the historical data to help us to estimate the probability of occurrence of certain number of events. Again, the same tossing of coin example, right? So if you have already tossed the coin 100 times, and out of 100 times you got heads 80 times and tails 20 times, and you are going to toss the coin for the 101st time. So when you do that, so you have some historical data to back up your probability estimation with regard to occurrence of a particular event, right? So probability of getting a head when we toss the coin for the 101st time will be much higher than the probability of getting a tail. So it will not be 50-50% because we have some historical information to back up our decision, right? So we have already seen out of 100 times, 80 times we have got heads, and it's only 20 times that we have got tails, right? So the same way, as I told you, we will have some kind of an historical information or historical performance to really back up for our estimation of probability of occurrence of certain number of events. So we have probability distributions for both discrete as well as for continuous data. So discrete data probability distributions, the most famous ones are the binomial distribution and the Poisson distribution. So binomial distribution, as the word itself suggests, the binary discrete data would follow binomial distribution. And we all know that binary discrete data would be better represented by the metric called proportion. So proportion is the primary metric for binomial distribution. And then we have Poisson distribution. So count discrete data would follow Poisson distribution. And we all know that Poisson distribution would be represented by a metric called average, which will be denoted by lambda, right? So average is the primary metric for Poisson distribution. And then under continuous data probability distribution, we are going to look at the most famous probability distribution called normal distribution. So normal distribution, we all know, is represented by a symmetric bell curve, right? So symmetric bell curve is the resultant output of a histogram. So when we connect the midpoints of all the adjoining bars in a histogram, and if we happen to get a symmetric bell curve, then we will say that the data distribution is normal. But then if you have some outlier value in the data set, due to which the bell curve is skewed. So it has a longer tail either on the right hand side or on the left hand side. We would call that as a non-normal distribution, right? So we will look at normal distribution in a short while. First, we will uh, just look at binomial and Poisson distributions, right? So let me go to the exercise file and then we'll click on the next sheet titled binomial. So as I have done for most of the statistical concepts, so I given the steps to solve binomial distribution exercises using the Excel formula as well as using Minitab. But then as I told you, we are also going to look at how to input the values in our template here and get the answers, right? So you don't have to really apply any formula if you are using the template. And we are also going to look at how to leverage the artificial intelligence tool in order to perform all these statistical exercises calculations, right? So let us move on to the exercise number 1. So it says that the defective percentage of a production process during the last 12 months is 3%. So this is the historical information that has been given to us. What is that? The defective percentage of a production process during the last 12 months is 3%. So with this information, we have been asked to estimate the probability of identifying the following number of defectives out of a sample size of 200, right? So first and foremost, so we have 3 sections to this particular exercise. Section A is asking us to estimate the probability of getting exactly 5 defectives out of 200 samples. The second one is at most 10. The third one is at least 10. So we will look at what is at most and what is at least. But then before that, how do we know that this is a binomial distribution exercise? So that is the first question, right? So since this particular exercise appears under binomial distribution header. So we know that this exercise has to be dealt with applying the binomial distribution logic. But then if this had been an independent case scenario, then how will you identify that this is a binomial distribution exercise, right? So for that, we need to first and foremost identify the historical performance metric that has been given, or in other words, we need to identify the event of interest. So what is the event of interest as far as this exercise is concerned? We are talking about defective percentage as the historical performance metric, and we have been asked to estimate the probability of identifying a certain number of defectives, right? So probability of obtaining certain number of defectives. So the event of interest will be occurrence of defectives. So event of interest will be occurrence of defectives. Now this occurrence of defectives, what type of data it will be? So when we inspect a sample unit, as I told you, sample unit can either be defective or non-defective. So when we talk about occurrence of defectives, it is a binary discrete event, right? So when we inspect a sample unit, the sample unit can turn out to be either defective or non-defective, and hence occurrence of defectives can be considered as a binary discrete event, right? So this will be a binary discrete event. So that is the first thing that we need to understand. So what is the data type of the event of interest? So if it is like binary discrete event, then we can apply the binomial distribution logic to solve that particular case scenario. Another piece of information which would confirm that this is a binomial distribution exercise is the historical performance metric. So what is the historical performance metric? The historical performance metric is in terms of defectives percentage. Again, defectives percentage is a binary discrete metric because we already seen accuracy percentage as an example for binary discrete metric. So accuracy percentage, the opposite is defective percentage, right? So as I told you, when we inspect a sample unit, the sample unit can either be defective or non-defective. Non-defective is what you would call as accurate transaction. So when accuracy percentage can be a binary discrete metric. Obviously, the defective percentage can also be a binary discrete metric, right? So historical performance in terms of defective percentage, which is a binary discrete metric, right? And this is given as 3%, right? The historical performance value is 3% for the last 12 months. So as I told you, whenever the input value is given in terms of a percentage value, so we need to convert that in terms of decimals before applying the same in the formula, right? So whether it is Excel formula, whether it is my template, whether it is Minitab dialog box, so wherever you are going to input all these values, so percentage values have to be converted and we need to input them as a decimal value. So we should not forget that. So 3% will be written as 0.03. So 3% will be fed into the formula as 0.03. So event of interest is a binary discrete event. Historical performance metric is also a binary discrete metric, and hence we need to apply binomial distribution logic to solve this exercise. So this is how we would need to identify the relevant probability distribution logic to solve a given case scenario. Now let us look at the first section, right? So I will also incorporate the sample size or number of trials. So it will be denoted by small n. So we all know small n is the notation for the sample size. And here the sample size will also be referred as number of trials, right? So number of trials is given as 200, which is a common input value given in the main question itself, right? So sample size or number of trials will be 200 and the historical performance given in terms of defectives percentage is 3%. Now, the first section, it says equal to 5. So what do you mean by equal to 5? What is the interpretation of this? When I say equal to 5, this is nothing but we need to estimate what is the probability of obtaining exactly 5 defectives out of 200 samples. So this is the meaning of equal to 5. So what do you mean by equal to 5? Equal to 5 is nothing but what is the probability of obtaining exactly 5 defectives out of 200 samples. So that is the question asked, right? So this we need to write in terms of a probability notation, right? So this particular question that I have framed has to be written in terms of a probability notation, which we all need to understand. It's very simple. So when we write the probability notation for this question, so we will start with capital P. So capital P stands for probability. So P of x equal to 5 would indicate that we are estimating probability of obtaining exactly 5 defectives out of certain number of samples, right? So when I write P of x equal to 5, so it would indicate that we are estimating the probability of obtaining exactly 5 defectives out of certain number of samples. So this is how I will write the probability notation, right? So for equal to 5, it will be P of x equal to 5, right? So I can straight away apply the Excel formula for binomial probability and estimate the value. So the binomial probability Excel formula will be equal to binom dot dist equal to binom dot dist and then open bracket. So again I repeat, so if you find this calculation logic to be slightly difficult to understand, absolutely no issues. So you can learn how to input the values in the template and interpret the answers. But try your level best to understand this calculation logic. So I'll also go very slow. I'll also keep it very, very simple as well, right? So the Excel formula will be equal to binom dot dist and we need to open the bracket. So it will ask for certain parameters to be fed in. So these are the input values that we need to provide in this formula. So first it is asking for number. So number is nothing but the x reference value in the probability notation. So in the probability notation, if you see, the X reference value is 5. So P of X equal to 5. So number is the number of the event of interest for which we are estimating the probability, right? That is what the number actually indicates. So here it is simply the X reference value in the probability notation. So we have written it as P of X equal to 5. So number will be 5. And put a comma. Without leaving any gap, we need to provide the next input value. So it is asking for trials. So trials is nothing but the sample size. So what is the sample size given in the exercise as common value, which is 200, right? So this 200 is common for all the three sections, right? So that's why I told you it's a common value. Now put a comma, and then it is asking for probability. So without leaving any gap, probability is nothing but the historical performance proportion of that binary discrete event, right? So what is the proportion of that binary discrete event which has been given as the historical performance? So this is given in terms of defective percentage, which is 3%. And as I told you, when you input that value in a formula, we need to convert the percentage value in terms of decimal, right? So probability would reflect the historical performance value, which is 3% that has to be entered as 0.03, right? And then put a comma, and the final parameter is cumulative. So cumulative, there are only two options, true and false. For this particular scenario, give the cumulative option as false. I will let you know when to give cumulative as true. That's it, right? You need to close the bracket and then press enter. So you'll get the final answer. Now this 0.1622, so we need to interpret, right? So we need to provide the inference as a statement here. So what will be the inference? So we need to convert this decimal probability value in terms of percentage so that your leadership will be able to understand this better. So there are 16.22% chances of obtaining exactly 5 defectives out of 200 samples. So this will be my final inference. So there are 16.22% chances of obtaining exactly 5 defectives out of 200 samples, given the historical performance for defective percentage as 3%, right? So that information is the key. So defective percentage being 3%, we have only 16.22% chances of obtaining exactly 5 defectives out of 200 samples, right? So we will see how to solve all these exercises using Minitab and also how to use our template to get the answers after we solve all these three sections pertaining to exercise number 1, right? So moving on to
Sridhar.
the next section. Yes.
So sorry to interrupt, Sridhar.
Yeah.
Could you help with the actual basic mathematical formula for what you have just written here in Excel?
You
If
want the mathematical formula?
it'll better connect to what we are solving actually.
No,
If if you
it
have
is
it.
in terms of combination. You need to know permutation and combination.
Okay.
Okay, so it will be like sample size to the combination of R, NCR, right?
Mm-hmm.
And then P to the power of R, 1 minus P to the power of N minus R. So this is a mathematical formula. So no one has asked me about the mathematical formula, even though we all learned, using the mathematical formula. So when we
Mm-hmm.
actually got introduced to all these concepts, right, in the year 2006, that's when I
Mm-hmm.
did my black belt. So
Okay.
I did it in Indian Statistical Institute.
I see.
So they kind of, they follow that old way of teaching people, right? So they go by that formula method, right? So
Okay.
we didn't actually get introduced to any Excel formulas at that time. So Excel formulas and all kind of a self-learning later on, right? So
Okay.
we all got introduced only to this mathematical formula and we solve all these exercises at that point of time. After
Oh,
that,
okay.
nobody has even asked me about what is the formula to,
Okay.
perform these calculations. But
Okay. Okay.
academically interested, I can provide you offline, right? So this is the formula, NCR into p to the power of r into 1 minus p to the power of n minus r. So this is the formula for estimating the binomial probability. But then
Okay.
it will be too technical for people to understand. Already, people wouldn't have been familiar with all these number games, right? So they would
Mm-hmm.
find it slightly difficult even to understand these things. That's why I repeatedly tell them that please don't worry, because I've seen people getting, totally stressed looking
Yeah.
at all these calculations, right? So I just used to tell them that no need to worry. We have the templates provided to you, so you just use the template, input the values and get the answer. The
Exactly.
worst scenario, right? Try to understand the calculation logic, at least try to see if you can understand how to apply the Excel formula and perform the calculation. But
Okay.
worst scenario, you can just use the template. But mathematical
Okay.
formulas will be too difficult for people to really understand, right? It will
I,
become
I I
too
understand.
dry for
I
people
just
to understand.
asked for my own understanding,
No,
just
that
to
I can
correlate.
because variance and also a simple formula. Because
Yeah,
variance, I
right.
had to
Right.
introduce that mathematical formula because
Mm-hmm.
we need to understand the concept of
Mm-hmm.
variation, right? So otherwise, people wouldn't have understood that variance cannot take negative values because
Yeah.
the formula itself is very clear. So we square all the deviations. So even if it is a negative deviation, when we square it, it will become positive. So people can understand, okay, variance and standard deviation cannot take negative values. So that's a very
Mm-hmm.
important, pointer with regard to
Exactly.
variance and standard deviation. So that's why I introduced mathematical formula there,
Exactly. Okay.
right?
Okay. All right. No worries.
Okay.
Thank you. Thank you,
Let
Sridhar.
us keep it very simple. No, I will just show you how to, kind of solve all these things using our template. But to the
Yeah.
extent possible, try to apply the Excel formula, try to understand how to apply the Excel formula. So
Yeah.
even in the final assessment, as I told you, right? So there is no need for you to apply the formula and
Mm-hmm.
spend time on that, right? So it's
Yeah.
always
Yeah.
better to use the template.
Templates. Yeah. Yeah. Right.
Yeah.
Okay. Thank
Okay.
you, Sridhar.
Yeah.
Yeah.
No problem. Yeah. The second section. So it says utmost 10. So what do you mean by utmost 10? Utmost means what? What is the meaning of utmost?
It should
When I
Maximum.
say,
reach till 10, but not more
yeah,
than that.
yeah, exactly. So maximum 10, right?
Maximum.
Utmost 10 means maximum 10. So what is this question? How to interpret this? So what is the probability of obtaining maximum 10 defectors out of 200 samples, right? So this is the question. So what is the probability of obtaining maximum 10 defectives out of 200 samples? So it should not exceed 10, as simple as that. So for all these, statistical exercises, it's always better to draw a diagram. So even though it can be a crude diagram, but just for our own understanding, nothing else. No one is going to, give us extra points for drawing the diagram. So this is basically for our own understanding. So what I'm going to do is I'm going to draw a horizontal scale. So we have the samples from 0 to 200, right? And the first one, we estimated the probability of getting exactly 5 defectives out of 200 samples. Second one, we have been asked to estimate the probability of getting maximum 10 defectives out of 200 samples. So when I say maximum 10 defectives, right? So it can be 0 defective, can be 1 defective, it can be 2 defectives, 3 defectives, 4 defectives, up to 10 defectives, right? So basically, we need to estimate the area or probability to the left of this value 10, correct? For the second scenario, when you say at most 10, so it means that we need to estimate the probability of getting maximum 10 defectives. That means we will not exceed 10, right? So when you say what is the probability of getting maximum 10 defectives, it can start from 0 defective, correct? So it can start from 0 defective plus 1 defective plus 2 defectives plus 3 defectives up to 10 defectives. So if you look at this diagram, so basically we need to estimate the area to the left of this value 10. So area, probability, these terms can be used interchangeably. So we need to estimate the probability pertaining to the area to the left of 10, right? So in terms of probability notation, how can I write this? So if you look at the first scenario, when we obtain the probability of getting exactly, 5 defectives out of 200 samples, I wrote the notation as P of X equal to 5. Now for at most 10, so when we need to find out the left-hand side area to this value 10, so how can I write the probability notation for this scenario? So P of
Less
X
than equal to,
less than or equal to 10. Very
yeah,
good. So less than or equal to 10. So this is the notation I will use for the second scenario, at most 10, right? So it's basically P of X is less than or equal to 10, which we need to find out. And this we can actually expand. So P of X less than or equal to 10 is nothing but, as I told you, P of X equal to 0 plus P of X equal to 1 plus P of X equal to 2 up to P of X equal to 10. So this is the expansion of this, right? So when I write P of X less than or equal to 10, it is nothing but summation of all the individual probability values from 0 to 10, because we are trying to find out the left-hand side probability to this particular value 10. So that is the second scenario, at most 10, right? So instead of finding out individual probability values from 0 to 10 and then summing it up, so we have a provision to apply the Excel formula and straight away get this value, straight away get the final answer for P of X less than or equal to 10. So let me just show you how to calculate this. So then in terms of probability notation, we are trying to find out P of X less than or equal to 10. And again, I apply the Excel formula is equal to binom dot test open bracket. So what will be the number here for this scenario? So what will be the X reference value? Number will be, come on, tell me,
10.
10, right? 10 comma, and trials will be, these are all the common values, right? So the sample size is 200 and the historical performance value is 0.03. And now coming to cumulative. So since we would need to add individual probability values from 0 to 10 for this second scenario, we need to give cumulative as true. Cumulative means summing up some individual values, right? Since we are supposed to sum up the individual probability values from 0 to 10 for obtaining P of X less than or equal to 10, so we need to provide cumulative as true. So in the first one, we didn't actually sum up anything. We just found out probability for that point, that is X equal to 5, right? So what is the probability of getting exactly 5 defectives is the first question. So since we didn't add any individual probability values there, we found out the individual probability value for P of X equal to 5. So we gave cumulative as false. But here, when it is P of X less than or equal to 10, we are actually summing up the individual probability values from 0 to 10. And since we need to provide directions to Excel that it is supposed to add the individual probability values from 0 to 10, we need to give the cumulative parameter as true, right? So this is how we need to differentiate. So cumulative false means X equal to 5. X equal to some value, cumulative will be false. X less than or equal to some value, cumulative will be true. So that is the generic, criteria that you can adopt for this cumulative parameter. So we need to round this off to 4 decimal places and we get the answer as 0.9599. So what will be the inference? This is very, very important, because if you are going to tell your leadership that P of X less than or equal to 10 is 0.9599, they will not be able to understand anything. So we also need to come up with the inference in a layman language, right? So the inference will be there are, so we need to convert this in terms of a percentage value. So there are 95.99% chances of obtaining maximum 10 defectives out of 200 samples, right? So there are 95.99% chances of obtaining maximum 10 defectors out of 200 samples. So as I told you, this P of X less than or equal to 10 is the summation of the individual probability values from 0 to 10. So we will also find out whether this particular statement is true or not. So what I'm going to do, I'm going to obtain the individual probability values from 0 to 10 and sum it up to see whether I'm getting the same answer, 0.9599, right? So this is P of X equal to 0. This is P of X equal to 1 up to P of X equal to 10, right? So now I can find out what is the probability of X less than or equal to 10. So P of X less than or equal to 10. So let me obtain the individual probability values for all these numbers from 0 to 10. So again is equal to binom dot test, open bracket. So the number will be, I'll just provide the reference so that I can copy paste the formula for all the other values as well. Comma, trials will be common 200. Historical performance is also common 0.03. Since I am finding individual probability values from 0 to 10, so I will give cumulative as false for this, right? So now I can simply copy paste this formula up to 10 and I can sum it up. So it's equal to sum of all these individual probability values from 0 to 10 and round this off to 4 decimals, you get the same answer, 0.959, right? So it proves that P of X less than or equal to 10 is nothing but summation of the individual probability values from 0 to 10. Fine. Now let us move on to the third scenario. So what is the third scenario? Third scenario says at least 10. So what do you mean by at least 10?
Minimum 10.
Minimum, right? So this is exactly opposite to the second scenario that we just now saw. So how we should interpret this? What is the probability of obtaining minimum 10 defectors out of 200 samples? So this is the question asked, right? Now, in terms of notation, at least 10, how will you write the probability notation? So looking at this diagram, right? So which area I need to shade for the third scenario, or which area I need to estimate for the third scenario?
I think
10
right hand
and
side.
Right
above.
hand, the right hand side area to this value 10, right? So this area, fine. So in terms of notation, how will I write this? P of X. What is the symbol I need to put if you want to find out the right hand side area to 10? So minimum 10 means it will not be less than 10. So it will be 10 and above. And
Greater
it
than
cannot
equal.
exceed 200 because 200 is the sample size.
Equal 10.
What is
Greater
this?
for
What is
Greater than
greater
equal
than
to.
or equal? Very good. So P of X greater than or equal to 10 is what we need to find out for the third scenario. And if you want to expand this in terms of individual probability values, this will be P of X equal to 10 plus P of X equal to 11 plus P of X equal to 12 up to P of X equal to 200. Because 200 is the sample size. We cannot go beyond that, right? So 200 is the sample size. So this is how I would expand P of X greater than or equal to 10. And that is exactly what I need to find out for the third scenario. But then Excel and Minitab can provide probability values only for equal to and less than or equal to scenarios, right? Excel and Minitab can provide probability values only for equal to and less than or equal to scenarios. It cannot give probability values for greater than or equal to scenario. So what we need to do, we need to convert this greater than or equal to into less than or equal to. So how I am going to do that? So for that, we need to use a probability property which says the sum of the individual probability values from 0 to 200 in this particular case will be equal to 1. So this is a standard probability property, right? It says the sum of the individual probability values from 0 to 200 in this particular scenario will be equal to 1. So if you are going to sum up all the individual probability values, right, like this, from 0 to 200, the answer will be 1. Right? So even if the sample size is 100, then it will be 0 to 100. The answer will be 1. So the individual probability value will get will get distributed, not equally distributed, will get distributed, right? So that the total probability value will be equal to 1, right? That is the probability property, right? Using this probability property, I'm going to convert this greater than or equal to into less than or equal to. So as per probability property, so P of x equal to 0 plus P of x equal to 1 plus P of x equal to 2 up to P of x equal to 200. So the entire stretch, right, from 0 to 200 will be equal to 1, right? Now P of x equal to 0 to P of x equal to 9 can be written as one probability notation, P of x less than or equal to 9, correct? So P of x equal to 0 up to P of x equal to 9 can be written in one probability notation as P of x less than or equal to 9. So less than or equal to 9 will contain individual probability values from 0 to 9. Since I want to find out the conversion for greater than or equal to 10. So I will have that as well. P of x greater than or equal to 10. So P of x greater than or equal to 10, as we saw just now, will contain the individual probability values from 10 to 200, right? So 0 to 9 is covered in this notation, P of x less than or equal to 9. 10 to 200 is covered in this notation, P of x greater than or equal to 10. So summation of these two notations will be equal to 1 as per the probability property. Now I can find out the equivalent for P of x greater than or equal to 10. So I need to take P of x less than or equal to 9 to the other side. So this will be 1 minus P of x less than or equal to 9. So this is how we need to convert greater than or equal to scenario into less than or equal to scenario and obtain the answer, right? So since Minitab and Excel can provide probability values for equal to and less than or equal to scenarios and not for greater than or equal to scenario, we need to convert greater than or equal to into less than or equal to by applying the probability property which says the sum of all the individual probability values for a given scenario will be equal to 1, right? So what I'm going to do, I'm going to split this into two components. So P of x greater than or equal to 10, let me expand this. So that will give you a better understanding. So this will be P of x equal to 10 plus P of x equal to 11 plus P of x equal to 12 up to P of x equal to 200, right? And then we have P of x less than or equal to 9, right? Which will be P of x equal to 0 plus P of x equal to 1 plus P of x equal to 2 up to P of x equal to 9. So this plus up to P of X equal to, right? So I know that, so P of X equal to 0 till P of X equal to 200 will be equal to 1 as per the probability property, right? So this will be P of X equal to 200 will be equal to 1. So splitting this into two components, I can write this as P of X less than or equal to 9 plus P of X greater than or equal to 10 will be equal to 1. So P of X less than or equal to 9 will cover individual probability values from 0 to 9, and P of X greater than or equal to 10 will cover individual probability values from 10 to 2, right? So both the components put together, the sum will be equal to 1. So now I can convert. So P of X greater than or equal to 10 will be rewritten as 1 minus P of X less than or equal to 9. So this can be treated as a standard notation. So whenever we encounter this greater than or equal to scenario, so this is how we need to perform the conversion for a discrete probability distribution case scenario, right? So the standard conversion will be something like this. P of X greater than or equal to R will be 1 minus P of X less than or equal to R minus 1, one number less than the original value. So this is the standard conversion that we can consider. So we don't have to really come up with this kind of a calculation, this kind of a conversion, right? So we can have the standard conversion, which is written in terms of R and R minus 1. So we can use that for all these greater than or equal to scenarios for a discrete probability distribution case scenario. So here P of X greater than or equal to 10 will be 1 minus P of X less than or equal to one number less than 10, which is 9, right? So for this, we can estimate the probability value. So we can put 1 minus binom dot dist open bracket. So what will be the number? P of X less than or equal to 9. So the number will be, the X reference value will be 9, comma, the number of trials 200, the historical performance 3%, and cumulative for less than or equal to will always be true. That's it. Round this off to 4 decimals and then provide the inference. Right, so what will be the inference? So there are 8.08% chances of obtaining at least 10 defectives out of 200 samples, given the historical performance of defectives to be 3%. That will be my final inference. Fine. So let us look at how to solve all these three sections using Minitab. And then I will also show you how to use our template to solve these, exercises. And we'll also look at how to apply the AI tool to perform the calculations, right? So let me go to Minitab. So in Minitab, so we are going to use this tab, CALC, Calc. So just click on this Calc tab at the top. So you'll get to see the probability distributions as one of the menu. So you have a host of probability distributions pertaining to both discrete and continuous data. So from this list, we need to select binomial, right? So the dialog box will open. So for the first one, where we need to estimate the probability of getting exactly 5 defectives, right? So when it is a scenario such as P of X equal to some value, so we need to choose the option probability. Just how like how you would give cumulative parameter as false, right? When you apply the Excel formula for P of X equal to some value. So in Minitab, when you are trying to solve the probability for P of X equal to some value, we need to choose the option probability. So cumulative probability as the option will be chosen for P of X less than or equal to some value, right? So for this, we will choose probability and provide all the input values. So number of trials, 200, the sample size, and probability of success is nothing but the historical performance value. So here we are talking about the historical performance of the defectives. So defective proportion is 0.03. So here again, we need to ensure that we provide the defective proportion in terms of a decimal value. And then since we need to obtain the probability for one single value, so we can choose input constant. And here we would provide the X reference value for which we are estimating the probability. So getting five numbers of defectives. So here the input constant will be 5. And then we need to click OK and get the answer 0.1622. And this is exactly what we got applying the Excel formula, right? For the second one, again go to calc, probability distributions, binomial. So for the second one, since it is P of X less than or equal to some value, so we need to choose the option cumulative probability. So the input values or the standard input values can be retained as it is, like number of trials and the defective proportion. And the input constant will be the X reference value, which is 10 for the second scenario. So P of X less than or equal to 10 will be 0.9599, rounding it off to 4 decimals. And for the third one, first we need to find out P of X less than or equal to 9, and then come to Excel and subtract that value from 1. So that is the calculation we need to do. So again, go to calc, probability distributions binomial. So we can retain it as it is. Only thing is the input constant value needs to be changed to 9. So we are finding out P of X less than or equal to 9, which is 0.9192. So this has to be subtracted from 1. So 1 minus 0.9192. So you get 0.0808. So sometimes Excel is much better than Minitab, right? So Minitab, we can only get the answer for P of X less than or equal to 9. So we need to come to Excel and then subtract that value from 1. Whereas in Excel, we can write the formula straight away, 1 minus binom.dist, and obtain the final answer. So in our template, it is going to be very, very, very easy. So just understand how to input the values in the template, right? So the template is given right below a couple of exercises that we are going to solve under binomial distribution. So for this first exercise, so what is the historical proportion of defectives? So what is the value that we need to feed in here? So what is the historical proportion? 0.03. So what is the sample size or number of trials? 200. And for the first one, what is the value for which we need to estimate the probability? 5. Right? X equal to 5. And here we need to provide the status symbol or the status, which is equal. P of X equal to 5, right? So equal is the option that we need to choose from the drop down. So you get the binomial probability, 0.162. So simple. So no need to apply any formula here. For the second scenario, so we can retain the historical proportion value and the number of trials, right? But the value for which we are estimating the probability changes here. So we are going to estimate the probability of obtaining maximum 10 defectives, right? So we need to change this to 10, and the status would be at most for the second scenario. So at most 10, 0.9599. And the third one, it is at least 10. So 10 also can be retained, but then we need to change the status to at least. So there is no need for us to use the probability property, convert that greater than or equal to into less than or equal to, and all those stuff, right? So straight away you'll get the final answer here. Just change the status to at least as given in the question. That's it. You get the final answer, 0.0808. So simple, right? So you don't even need to apply any logic here. Just understand how to input the values in the input section and interpret the answer that you will get in the output section. So simple. But then if you are using the AI tool, so how to solve this? So you go to Perplexity and I will present the first scenario. So what is the probability of obtaining exactly 5 defectives out of 200 samples given the historical defective rate as 3%. So moment I provide the prompt, so the AI tool will calculate and provide me with the final answer, right? So 0.1622. That's exactly what we got, right? Or 16.22%. Next one, what is the probability of obtaining at most 10 defectives out of 200 samples given the historical defective percentage as 3%. So it is thinking 0.9599, right? So that's the answer. We also got 0.9599 is the correct answer, or 95.99%. And the third scenario, what is the probability of obtaining at least 10 defectives out of 200 samples given the historical defective percentage as 3%. Give you the final answer, 0.0808 or 8.08%. So AI tool also will be very easy to handle, provided you give the correct prompt. And one important thing, as I told you yesterday, so we need to look at using the advanced version of the AI tool. Some of the basic versions, they don't provide the correct answer. So let me just tell you that clearly. So as far as our assessment is concerned, so please, use the template that I have provided. So please don't depend on the AI tool. So if you're using a basic version, then you may not get the right answer. So still, some more progress needs to be done with regard to the AI tools. But the advanced versions are giving the correct answer. The basic versions, we still have some problem. So we need to be careful with that. So till such time, always, use the template. It will be very easy. And move on to the next exercise. So this is a practical scenario that you would face in your own process as well. So what is the scenario? So in process ABC, 93% of the units produced adhere to the customer specifications during the last 12 months. That means 93% is the accuracy percentage. When I say, 93% adhere to the customer specifications, it means 93% is the accuracy percentage. This is the historical performance data that we have. Now, the second part of the question, it says if the customer target is 95% adherence, estimate the probability of meeting the customer target if the monthly production is 100 units. So if the customer target is 95% adherence, estimate the probability of meeting the customer target if the monthly production is 100 units. So first and foremost, we need to find out which probability distribution logic we are supposed to apply for solving this case scenario, right? So let me look at the event of interest. Event of interest will be, so if you want to reproduce the same language that is given in the question, the event of interest is adherence to the customer specification. So what is the data type of this event of interest? So if you are going to inspect a unit item, the unit item can either adhere to the customer specifications or it may not adhere to the customer specification. Only two options available, right? So it can either adhere to the customer specifications or it may not adhere to the customer specification. So adherence to customer specification will be a binary discrete event, right? And what is the historical performance value that's given to us in the question? So the historical performance is in terms of percentage adherence to customer specification, right? And this is a binary discrete metric. So as I told you, when you inspect a sample unit, the sample unit can either adhere to the customer specifications or it may not adhere to the customer specifications. So if you want to calculate this metric, so what is the formula that you would apply? So the numerator, we will have the number of units adhering to the customer specifications divided by the total number of units inspected. So if you see, this formula would fulfill all the three conditions that we saw for binary discrete data. So percentage adherence to customer specification is nothing but the accuracy percentage, as I told you. So this will be a binary discrete metric. And hence we need to use binomial distribution logic to solve this exercise. So this is how we need to identify the appropriate probability distribution logic we are supposed to use for solving a case scenario. Now, having identified that this is a binomial distribution exercise, so let me also kind of provide the input values here. So the historical performance data pertaining to percentage adherence to customer specifications is 93%, or in terms of decimals, this has to be written as 0.93. And what is the sample size here? What is the sample size given in the exercise?
100.
100. So that is the monthly production. So sample size is given as 100. Right? So for solving a binomial distribution problem, so we need to have three input values. So what are the three input values? One is obviously the historical performance proportion value for a binary discrete event. The second one, the sample size or the number of trials. And the third one, the value for which we are supposed to estimate the probability, right? So these are the three input values that we need to have for solving a binomial distribution exercise, correct? But then as far as this particular scenario is concerned, exercise number 2, the historical performance has been given, right, which is 0.93. Number of trials or sample size is also given, which is 100 units. But the value for which we are supposed to estimate the probability is not given as a whole number. It is given as a percentage value. It says if the customer target is 95% adherence, estimate the probability of meeting the customer target, right? So this we need to convert in terms of a whole number. So when we have 100 units as the monthly production, out of 100 units, how many units minimum needs to adhere to customer specifications if we are to meet the customer target of 95% adherence? So given the monthly production as 100 units, so what is the minimum number of units that are supposed to meet the customer specifications if we need to ensure that the customer target is met, which is 95% adherence. So how many units minimum needs to adhere to the customer specifications if we need to meet 95% adherence?
95.
95.
95 out of 100, right? So simple. That's why I gave the sample size as 100 so that the calculation becomes easy. So it is 95 minimum, or at least 95 out of 100 needs to adhere to the customer specifications for us to meet the customer target of 95% adherence, right? So at least 95 is what we need to find out for this particular case scenario. So let me provide that explanation here. So in order to meet the customer target adherence of 95%, we need to ensure that at least 95 units. So how did I get 95 units? This is 95% of 100 units. Out of 100 units, adhere to the customer specifications.
Niti,
Right? So we need to find out the probability for at least 95. So at least 95. So what will be the probability notation for this P of at least 95? You guys should be able to tell. At least 95, what will be the probability notation? We saw this for the first exercise, right?
X
Third
equals
section.
5. X equals 95.
No, X not equal to. What is the symbol that I need to put? At least 95 means minimum 95 units, right? So minimum 95 units means it will be 95 and above, correct? So it will be 95 and above is what we need to find. Greater than or equal to. So even if you achieve 95, it's fine. You'll be able to meet the target. So 95 and above, that means you'll be meeting the customer target. So X is greater than or equal to 95. So X equal to 95 means you are finding out the probability for 95 units adhering to the customer specification, right? So 95 out of 100 units, adhering to the customer specification. But at least 95 is what we need to find, because you would be meeting the target if you are able to ensure that minimum 95 out of 100 meets the customer specifications, right? So it can be 95 units out of 100 or 96 units out of 100 or 97 units out of 100 and so on, right? So we can say that we are meeting the customer specifications. So at least 95 is what we need to find. So in terms of probability notation, this can be written as P of X greater than or equal to 95. And greater than or equal to, we cannot get the probability value in Excel or Minitab. So we need to convert this into less than or equal to. So how will you perform the conversion? This will be 1 minus P of, what tell me, X, 1 minus P of X. So you can
It's
see
less than equals 5.
less than or equal to, what is the value that I need to put here? So you can use this as a standard notation that I have given.
5.
5.
Pardon?
5.
Where is 5? 5
100
is not at all there. 1 minus P of X. You can use this particular notation that I have given here, right? This is the standard notation. Right?
4.
94. So P of X greater than or equal to R can be rewritten as 1 minus P of x less than or equal to r minus 1. So here we are talking about p of x greater than or equal to 95. So which can be rewritten as 1 minus p of x less than or equal to 94. One number less than 95. Right? So this is how I need to perform the conversion, right, of greater than or equal to into less than or equal to. So you can see this notation. So that's why I given the standard notation. So p of x greater than or equal to r can be rewritten as 1 minus p of x less than or equal to r minus 1. The same logic has been applied here. So p of x greater than or equal to 95 can be rewritten as 1 minus p of x less than or equal to 94. So for this, we can find out the probability value. So this will be 1 minus binom dot test open bracket. So what will be the number? P of x less than or equal to 94 means the number will be
94,
94, comma, number of trials,
100,
sample size is 100, comma, historical performance
0.93,
0.93, comma, cumulative will be
true.
true. That's it. So you need to round this off to 4 decimals. Right? 0.2914. So what is the inference? The inference is there are 29.14% chances of meeting the customer target of 95% adherence. Because the historical performance being 93%, we have only 29.14% chances of meeting the customer target of 95% adherence. So we don't stand a very good chance of meeting the customer target of 95% adherence. If it is at least 50%, we can say there is some chance of meeting the customer target of 95% adherence. 29.14, the chances are very low, right? So obviously we need to look at performing some process improvement initiative. So with the 93% adherence that we currently have, so we cannot comfortably meet the customer target of 95% adherence. So obviously we need to work on some process improvements. So in order to comfortably meet the customer target of 95% adherence. Right? So that's the kind of inference that we can come up with for this scenario. So if you are solving this using Minitab, so we will not get the final answer in Minitab, but we need to solve for p of x less than or equal to 94. And then we need to go to Excel and subtract that value from 1. So again, click on Calc, probability distributions, and then binomial. So we can retain cumulative probability. So the number of trials will be 100 and the historical adherence percentage will be 0.93 and the input constant will be 94. So we get p of x less than or equal to 94 as 0.7086 and this 0.7086 has to be subtracted from 1. 0.7086. So we get 0.2914. That's the correct answer. Fine. But then if you're using the template to solve this, so what are the input values that we need to feed in here? So historical proportion value will be written as 0.93 and then the number of trials or the sample size will be 100 and the value for which we are estimating the probability. So at least 95. So provide the value 95 here and at least status can be retained. So you'll get the final answer 0.2914. Right? So no need to worry about converting greater than or equal to into less than or equal to if you're using the template. But then how to solve this using our AI tool? So you just need to copy paste the entire problem. Right? Let me just copy paste the entire problem and then see whether we are getting the correct answer. says about 28%, right? So our output says it's 29.14%, but AI tool is giving the answer as 28%. There can be slight variation. That's what I told you. Cannot be totally dependent on the AI tool. Sometimes you'll not get the perfect answer. You can get roundabout that value. Fine. So better to use the templates to solve all these exercises. Fine. So this is about the binomial distribution exercises. So next we are going to move to the Poisson distribution exercise. So we have only one exercise containing some 3 sections. So the logic is going to be the same kind of logic that we applied for binomial distribution has to be applied for Poisson distribution as well, right? Only difference is there binomial distribution, the historical performance was given in terms of a proportion value for a binary discrete event. In a Poisson distribution, the historical performance will be given in terms of the average value for a count discrete data, right? Or a count discrete event of interest. So let me go through this exercise. So it says average production of a car manufacturer is 25 cars per day. So this is the lambda value, this is the historical average. So estimate the probability of production of the following number of cars. Again, we have been provided with some 3 sections equal to 25, at most 30, and at least 20. So first and foremost, we need to find out whether this is a Poisson distribution exercise. So for that, we need to identify the event of interest. So the event of interest, as we can see, is about the production of cars, right? Or the number of cars produced. Number of cars produced. So this is obviously a count discrete event. So number of cars produced can be mentioned only in terms of a whole number. It cannot be mentioned in terms of decimal. So this will be a count discrete event. And what is the historical performance? Historical performance is given in terms of average, right? Average, again denoted by lambda. So average will be 25 cars per day. So this is metric for count discrete data. So average is the metric for count discrete data. So we can understand that this is a Poisson distribution exercise. So this is how we need to identify, even though some of the things could be straightforward, but then we need to go through the steps and find out which probability distribution logic we are supposed to apply for solving a given case scenario. So the first section says equal to 25. So what is the meaning of this? What is the probability of producing exactly 25 units of car per day? So what is the probability of producing exactly 25 units of car per day? So in terms of probability notation, this can be written as P of X. What is the symbol that I need to put?
Equals.
Equal to 25. P of X equal to 25. So for binomial distribution, we applied the Excel formula is equal to binom.dist. So for Poisson distribution, we will apply the Excel formula is equal to Poisson.dist. And then open bracket. So X is nothing but the X reference value, which was given as number in that binomial distribution formula. So here it is given as X. X is nothing but the X reference value, which is 25. Mean is nothing but the historical average, right? Which is also given as 25. And cumulative for equal to will be false. So you need to round this off to 4 decimal places and provide the inference. So what will be the inference? The inference will be there are 7.95% chances of producing exactly 25 units of car per day. So this is the inference. Now moving on to the next section, at most 30. So what is the meaning of this? So we have been asked to estimate the probability of producing maximum 30 units of car per day. So what is the probability of producing maximum 30 units of car per day? So that is the meaning of at most 30. So in terms of probability notation, this can be written as P of X less than or equal to 30. So it will not exceed 30. So it will be less than or equal to 30. So we can apply the Poisson distribution formula is equal to Poisson dot test open bracket. So X reference value will be 30 for this, comma, mean is 25, and cumulative for less than or equal to, it will be true. That's it. Round this off to 4 decimals. And provide the inference. Inference will be, there are 86.33% chances of producing maximum 30 cars or 30 units of car per day. So there are 86.33% chances of producing maximum 30 units of car per day. And then the third section says at least 20. So what is the meaning of this? What is the probability of producing minimum 20 units of car per day? So what is the probability of producing minimum 20 units of car per day? So that is the meaning of at least 20. Right? So in terms of notation, this can be written as P of X greater than or equal to 20. But then Excel and Minitab cannot provide probability values for greater than or equal to scenarios. So we need to convert this in terms of less than or equal to. So this can be rewritten as 1 minus P of X less than or equal to one number less than 20, which is 19. The same logic, the same expression can be used here, right? P of X greater than or equal to R can be rewritten as 1 minus P of X less than or equal to R minus 1. So P of X greater than or equal to 20 can be rewritten as 1 minus P of X less than or equal to one number less than 20, which is 19. So for this, we can apply the formula. So this will be 1 minus Poisson dot test open bracket. So the X reference value will be 19, comma, the mean will be 25, comma, and cumulative for less than or equal to will be true. Okay, 0.8664, and we just need to provide the inference. So there are 86.64% chances of producing minimum 20 units of car per day. So there are 86.64% chances of producing minimum 20 units of car per day. Right? So if you want to solve this using Minitab, you can do so. So we need to again go to Calc and then choose probability distributions. And we need to click on Poisson in this list. Right? And for the first one, P of X equal to 25. So we need to choose the option probability and provide the historical average value here, which is 25. Choose input constant, and this is also 25. P of X equal to 25, so input constant also will be 25. So we get the value 0.0795. This is exactly what we got applying the Excel formula. The second one, at most 30. Again, go to Calc, probability distributions, Poisson, and we need to choose cumulative probability. So this will be P of X less than or equal to 30. And the input constant needs to be changed to 30. That's it, 0.8633. 0.8633. And the third one, first we need to find out P of X less than or equal to 19. So calc probability distributions Poisson. So everything else can be retained as it is. The input constant value will be changed to 19 and we get the value 0.1336. And this has to be subtracted from 1. So this will be 1 minus 0.1336, which is 0.8664. Right? But then if you're using the template, you don't have to use any formula here. So just provide the input values. So historical average is given as 25 units of car per day. And the first one, section A, the value for which we are estimating the probability is also 25 and the status is equal. So the answer is 0.0795. The second one, it is at most 30, which is 0.8633. Third one, at least 20, 0.8664. So easy, right? So I can also see how to use the AI tool. The
Sridhar,
person,
one question. If you go back to the exercise, it could be a silly question. Please excuse me for that.
no
If you
problem.
just scroll it up and go to the first question. So we are already manufacturing 25 cars per day, and the probability of production of 25 cars is too less.
Yeah, because see, when you estimate the probability, right, of producing exactly a certain value, it could be equal to the average value, but that will be the highest probability. Average will be the highest probability, right? But then the probability value has to get spread equally, or it may not be equally, but it has to get spread across the entire spectrum of values, right? The sample values, correct? The probability value. So we'll have to get spread, because the total sum will be equal to 1. So if you are going to sum up the individual probability values for the entire stretch, it will be equal to 1. So that being the case, so it will get distributed, right, to all the numbers. So 25 is just one value, correct? So even though, so what we can say is the 7.95 percentage as an individual probability value will be the highest, because we will have the highest probability for the number of occurrences, which is actually equal to the average value, right? So 7.95 or 0.0795 will be the highest probability value if you calculate the individual probability values from 0 to 100 or whatever, because sample sizes has got no relevance in a Poisson distribution, like binomial distribution. Right? So Poisson distribution, we don't have the sample size. So it can go up to infinity also. So beyond a certain value, so the probability, individual probability value will be 0, right? So we can actually calculate the individual probability values from 0 to say 50 or even 100. And you will be able to see that for 25, P of X equal to 25, the individual probability value will be the highest, because the average is 25 units per car. 25 units of car per day, right? So this 0.0795 for P of X equal to 25 will be showing the highest probability value, individual probability value, right? When we see other individual probability values, this will be the highest, but it has to get distributed across the entire spectrum of values, correct? So it can even go from 0 to 50 or 0 to 100. So the total sum can only be equal to 1, cannot go beyond that. So that being the case, it has to, distribute the probability values to the entire spectrum of the X reference values from 0 to 50 or even 0 to 100, right? So when we calculate the individual probability values, you'll be able to clearly identify that P of X equal to 25 will have the highest individual probability value, because the average is 25. That doesn't mean that we will have a greater chance, because here we are only talking about, probability of producing exactly 25 units of car per day,
So this
right?
means
Yeah.
that there is higher probability that there will be 24 cars or 26 cars.
No. 24 and 26 will have a lesser probability than 0.0795. That's what I am saying. So P of x equal to 25 will have the highest individual probability, because that is, equal to the average value, which is 25 units of car per day. So that will have the highest probability. So you can even, solve and see. So you let me just enter the value 0 to say 50. Or even 0 to 20. Let me see. If it goes beyond 20, then we will extend this further. So this will be Poisson dot test open bracket. I will provide this as reference, comma, 25, comma, cumulative for individual probability value will be false. So we need to change this to a number format. 4 decimals. So the first one itself is 0. Let me just copy paste. Right? So it has to be beyond this. Let me give up to 50. Let's see. Fine. So our 25, as we can see, it is the highest. So even though 24 is also showing the same number, 0.0795, but you can say 25, if you still expand, right? So 25, it will be the highest. So P of x equal to 25, we see the highest individual probability. Otherwise, on either side, if you see, the probability values are actually reducing. So if you go on the upper side, right, you can see 23, it's only 0.0763. 19, it's only 0.0415. And the other side, 26, it's only 0.0765, and then 0.0708, right? And beyond a certain value, it will become 0, as I told you. So from 47 onwards, it is showing as 0. And if you are going to sum all these individual probability values, it will be equal to 1. See, you can just round this
Right.
off, equal to 1. Right? Because it has to distribute, right? All these individual probability values. So it starts from actually 8, right? So till 8, we have 0 as the probability value. Only from 8, we have some, probability value getting displayed. So it has to, spread, or it has to distribute the probability values from 8 to 47, 8 to 46 in this case scenario, right? So that's why, the individual probability values, if you calculate, it will be far too less. So at 25, even though it tallies with the average, so just because it tallies with the average, we have the highest individual probability for that value. That's the only thing. So it doesn't mean that it will have a higher probability of occurrence. Clear? So let me go to the AI tool. So what is the probability of producing exactly 25 cars per day if the historical average is also 25 cars per day? So when you're using the AI tool, you don't have to really tell AI that it is a binomial probability or Poisson probability. It will understand by itself, right? Just post the question alone So it will provide the answer. Sometimes, as I told you, you won't get the right answer. See, here is one instance. So it's showing us 0.027, whereas the answer is 0.0795. So this is some of the discrepancies that we will face when we use the AI tool. Still, I think it's work in progress. Some of the advanced statistical exercises, we do get some incorrect answers, right? So it is actually, identified that the probability distribution is Poisson, but then it is showing the answer as 0.027, right? As we have calculated here, 0.027 is closer to 70, P of x equal to 70, not P of x equal to 25. Maybe we need to provide some other prompt, I don't know, but we don't get the correct answer sometimes. So let me just try for the other one, the second scenario. So what is the probability of producing maximum 30 cars per day if the historical average, or given the historical average, as 25 cars per day? See, again, it is not giving the correct answer. It's saying 96.4, whereas the correct answer is 0.8633.
I think the question does not have a production per day. Do we mention per day there?
Yeah, per day. Or probably I need to put PER day. I think it's not reading that properly.
I got the correct answer.
You got the correct answer. Okay.
AI
That's
gave
what I'm saying. Right? What is the prompt you gave?
I just copied the
Same question, is it? Or that itself is
I copied the question of the exercise.
Okay. Let me try out this. See, here again, get the incorrect answer.
If you remove per day, I think it
Okay.
will get the right answer. 30 cars, just 30 cars. Don't give per day.
Okay. Okay. We also.
No, historical you can give, but other
here.
you don't give. Yeah. The expectation don't give because we don't have that in the question. So here you can give per day. Let's see what happens.
Okay. No, still get incorrect answer. This is the problem. So I have tried out using this. Sometimes it gives the same AI tool gave me the correct answer. Right? So it's not like, we are getting incorrect answers each and every time. So the same AI tool gave me the correct answer when I tried this for the previous batch. The same prompt was given. It's not a different prompt. That's what I'm saying. So it's still not consistent, right? So we still have a long way to go as far as usage of AI tool is concerned with regard to the statistical exercises. Slightly risky. So that's why I don't recommend usage of AI tool, the final assessment. Always go for this template. Fine. So this is how, we will solve the binomial and Poisson distribution exercises. So now let us move on to the continuous data probability distribution, which is normal distribution. And this is a very, very famous continuous data probability distribution. As I told you yesterday, so we have host of continuous data probability distribution. Apart from normal, we have exponential, we have V-bull, log normal, Erlang, uniform, Pareto, so gamma distribution. So all these are continuous data probability distributions. But as I told you, the normal distribution is the most famous one. Most of the data distributions will be normal, right? If you have a continuous data set, unless and until we find some outlier in the data set, which will be an exceptional scenario. The ideal scenario is that we will always consider the process to be influenced by common cause variation alone, and the data distribution also will be normal. So normal distribution is a very famous continuous data distribution. And as I told you, the normal distribution will be represented by a symmetric bell curve. So moment you draw a symmetric bell curve like this, so it would mean that the data distribution is normal, right? So this is the symmetric bell curve. So symmetric bell curve means when we cut the bell curve into two equal halves, the left-hand side image will be the mirror image of the right-hand side. Then only you can call that as symmetric. And one more important thing is the primary matrices for a normal distribution are mean and standard deviation. So while proportion is the primary metric for binomial distribution, average is the primary metric for Poisson distribution. The primary matrices for normal distribution are mean and standard deviation. So for a normal distribution exercise, so you'll be provided with the historical performance in terms of mean and standard deviation, right? For a normal distribution exercise, the historical performance will be given in terms of mean and standard deviation, right? So just like how we saw, the historical performance was given in terms of a proportion value for a binomial distribution exercise and average value for a Poisson distribution exercise. For a normal distribution, the historical performance will be given in terms of mean and standard deviation. So before even we venture into normal distribution properties, we will look at what is called the standard normal distribution. So go back to the exercise file. So we will look at the standard normal distribution first, and then we will look at the properties of normal distribution. So the standard normal distribution. So what is the key property of standard normal distribution? So if you have a normal data set like this, right? So we have the data points like 65.3, 66.4, 65.9, etc. So let us consider this to be a normal data set. And if you want to convert this normal data point into a standard normal data point, then we need to apply the standardization formula. So Z is the notation that you would use for standardization. Z is the notation that you would use for standardization. So Z is equal to data point minus mean divided by standard deviation. So this is the formula that we would apply for standardizing the normal value. So what we need to do, first and foremost, when we have the normal data set, we will find out the mean and standard deviation for that normal data set. And with the help of mean and standard deviation, we will convert the normal data point into a standard normal data point. So using the standardization formula, it will be data point, which is 65.3 minus mean, minus 65.92 divided by standard deviation, which is 0.42. So when we apply this formula, we get the value, the standardized value as minus 1.47. So for 65.3, the equivalent standardized value is minus 1.47. Similarly, for 66.4, we apply the same formula, 66.4 minus 65.92 divided by 0.42 will give you 1.14. Now like this, if we standardize all these normal data points, we will get a standard normal data set. And for this standard normal data set, the mean will always be equal to 0 and standard deviation will always be equal to 1. So this is an important property of standard normal distribution. So that is why we are even touch basing on this. So for a standard normal distribution, the mean will always be equal to 0 and the standard deviation will always be equal to 1, right? So you can change the normal data set to any value. So let me just provide values in the range of 75 and odd. So you can see all the other values changing here except for mean and standard deviation for the standard normal distribution. So all these are formula driven, right? You can see All the other values, changing here, except for the mean and standard deviation for the standard normal data set, right? So this is an important property of the standard normal distribution. So when this particular logic was used, so it was used when people didn't have Excel and Minitab to obtain the probability values, right? So people were dependent on statistical tables to obtain the probability values. Now we have Excel and Minitab, so we can give any uh, combination of mean and standard deviation, you get the probability value for a given point. But in those days, people didn't have Excel or Minitab, so they were dependent on statistical tables to obtain the probability values. And statistical tables cannot contain probability values for all different combinations of mean and standard deviation. Practically impossible. So you'll have infinite combinations of mean and standard deviation values. So it is practically impossible for us to expect obtaining probability values for each and every combination of mean and standard deviation. So the standardized or the statistical tables will contain the probability values for the standard combination of mean and standard deviation, that is mean equal to 0 and standard deviation equal to 1. So what people used to do, so they used to convert the normal data points into the standard normal data point like this by using the standardization formula data point minus mean divided by standard deviation, and then they used to obtain the probability value for a given standard normal data point, and then they will always treat that as a probability value for the equivalent normal data point. That's how people used to find out the probability values in those days. But now we have Excel and Minitab. As I told you, it can give probability values for any given combination of mean and standard deviation, so there is no need for us to worry. But then this logic can be applied even in today's context. Say, for example, you want to assess the performance of your team. So the annual appraisal is coming up. So you want to understand or you want to stack rank the performance, the stack rank the team's, performance. And you have some three matrices. The three matrices have been considered for measuring the performance of each and every individual in the team. So what are the three matrices? It could be accuracy percentage, it could be time taken to process a unit item, and it could be average productivity. So let us assume these are the three matrices that you have actually fixed as the performance metric for the team, right? So you will have the team members, right? And you will have the values for all these three matrices like accuracy percentage, time taken to produce a unit item, and also the average productivity for the entire team, right? So when we have these three performance metrics and the values given for them, right, or the values provided for the entire team, so how can we stack rank? So stack ranking cannot be done just by adding all these three numbers. So you'll have a value for accuracy percentage, you'll have a value for the average time, you'll have a value for average productivity. So for a particular team member, we simply cannot add all these three numerical values and then come up with a cumulative value and stack rank. Why? Because all these three matrices have different units of measure, right? When the matrices have different units of measure, we all know we cannot simply add the numerical values and come up with the cumulative value. So what we need to do here, so we need to look at finding out the standardized values, right? So for a given accuracy percentage value, so we need to find out what is the equivalent standardized value. So for that, we'll use this standardization formula, data point minus mean divided by standard deviation. Similarly, for the average time, we need to find out the standardized value. And then for average productivity, we need to find out the equivalent standardized value. So for the entire team, we will have the accuracy percentage. So we need to calculate the mean and standard deviation. And for each of these accuracy percentage values, we will come up with the standardized value using this formula, data point minus mean divided by standard deviation. So once we have the standardized values calculated for all these three matrices, we can sum up all these standardized values and come up with the cumulative standardized value, right? Because the standardized values can be summed up and we will arrive at the cumulative standardized value. And based on this cumulative standardized value, we will stack rank the performance of the entire team, right? So even in today's context, we can definitely make use of this standard normal distribution logic. But then there's an important property of standard normal distribution. That's why I thought we need to introduce this. So moving on to the normal distribution properties, we are going to find out the area coverage under various sigma limits for a normal distribution. So whenever you talk about normal distribution, as I told you, you'll draw the bell curve. So let me draw the bell curve. And what exactly this area coverage under various sigma limits. So let me assume this to be a standard normal distribution. So we will have the mean at the center and the sample mean is denoted by the notation x bar. So x bar is 0 and standard deviation, which is denoted by small s. Small s is the notation for sample standard deviation. So that is given as 1, right? We are assuming this to be a standard normal distribution just for calculation convenience, nothing else, right? So mean and standard deviation can be any value. So we are assuming this to be a standard normal distribution. So let me have the values as -1 and +1, right? Now, I need to find out the area or probability between +1 and -1. So how can I do that? So the constraint here is Minitab and Excel cannot provide probability values for greater than or equal to scenario. It can provide probability values only for less than or equal to scenario. Or if you want to simply put it, so we will get probability or area to the left hand side of a value. So we will not get probability or area to the right hand side of the value, right? So that's what we have seen. So you'll get only the left hand side probability. So that is the constraint we have. Given this constraint, so how are we to find the area between +1 and -1 in this diagram? So this is a logical question. This has got nothing to do with any calculation. This is purely a logical question. So given the fact that we can obtain only the left-hand side probability or left-hand side area for a given point, so what I will do is first I will find out the entire area to the left of +1. So you'll also get area extending beyond -1, correct? And from that, if I'm going to subtract the left-hand side area to -1, then we will get the area between +1 and -1. So let me repeat this. So how will you get or how will you obtain the area between +1 and -1? So first and foremost, we will calculate the entire area, entire left-hand side area to this value +1. So you'll also get area extending beyond -1 here. So from that, if you are going to subtract the area to the left of -1, we will get area between +1 and -1. So this is the logic that I am going to follow for calculating the area between +1 and -1 for a normal distribution, right? So for calculating the area to the left of +1, so I can use the probability notation P of x less than or equal to +1. So you already seen how to use this probability notation. So left-hand side area means we need to provide the symbol less than or equal to. So P of x less than or equal to +1 is what we need to find out first. So for binomial distribution, the formula, the Excel formula was is equal to binom.dist. For Poisson distribution, it was equal to Poisson.dist. For normal distribution, it will be is equal to norm.dist. And then open bracket. So x will be the x reference value, which will be +1, comma. We are assuming this to be a standard normal distribution. So mean will be 0 and standard deviation will be 1. And cumulative for this continuous data probability distribution will always be true because you'll be dealing with mostly less than or equal to scenarios. So it will be true. So cumulative will be true. So we get the entire area to the left of +1. So from this, we need to subtract the area to the left of -1. So again, apply the formula is equal to norm dot dust, open bracket. Now the x reference value will be -1 here. Mean is 0, standard deviation is 1, cumulative will be true. Right? So this is the area to the left of -1. So when we subtract these two values, you get the area between +1 and -1. So in terms of notation, the probability notation, this is how we will write because we haven't seen this before. So you're getting introduced for the first time, the area between any two numbers. So how will you write this in terms of probability notation? Again, start with capital P, open bracket, -1 less than or equal to x less than or equal to +1 would indicate that we are calculating the probability between +1 and -1 or the area between +1 and -1. So this is the notation that I will write for indicating that we are calculating the area between some two values, right? Here it is +1 and -1. And if you subtract these two area values, you get 0.6827 in terms of percentage. It will be 68.27%. Just park this value. Next, we will find out area between +2 and -2. The same logic will be applied, right? So first we will find out the entire area to the left of +2. From that, if you are going to subtract the area to the left of -2, we will get the area between +2 and -2 for a normal distribution, which is 0.9545. In terms of percentage, it will be 95.45%. And then the area between +3 and -3. Again, we will find out the entire area to the left of +3. From that, if you are going to subtract the area to the left of -3, we will get the area between +3 and -3, which is 0.9973. In terms of percentage, it will be 99.73%. So it's important for us as a black belt to remember all these three values, right? So these are called as area coverage within various sigma limits for a normal distribution. So 0.6827 is the area coverage within one sigma limit for a normal distribution. 0.9545 is the area coverage within two sigma limits. That means +2 to -2 for a standard normal distribution. And the area coverage within three sigma limits is 0.9973 for a normal distribution. So +3 to -3, right? So what does these values actually indicate? So when I say that the process adherence to the customer specification is to the extent of 68.27% of the overall production, meaning out of the total number of units produced, only 68.27% are adhering to the customer specification. That means 68.27% units are accurate units. Then if you have such a low adherence, then the process is said to be functioning at 1 sigma level. We are slowly getting into the calculation of sigma level, right? So when the process adherence to the customer specification is to the extent of 68.27% of the overall production, then the process is said to be functioning at just 1 sigma level. So at 1 sigma level, we will have a non-conformance percentage of 31.73%. So 100% minus 68.27% will give you 31.73%. So non-conformance is what we would call as defects. So much defects are there in the process output, then the process is said to be functioning at just 1 sigma level. Similarly, if the process adherence to the customer specification is to the extent of 95.45% of the overall production, then the process is said to be functioning at 2 sigma level. So at 2 sigma level, what is the non-conformance? So our defect percentage, it will be 4.55%. Similarly, if the process adherence to the customer specification is to the extent of 99.73% of the total production, then the process is said to be functioning at 3 sigma level. So at 3 sigma level, the non-conformance or the defect percentage will be a mere 0.27%. And in 6 sigma, 3 sigma level is considered as average performance. So at 6 sigma level, the efficiency percentage will be 99.99966%. Of course, we have long-term sigma level, short-term sigma level, which we will see after the break. But then for now, just understand that if the adherence to customer specification is to the extent of 68.27%, then the process sigma level is only 1. If it is 95.45% adherence, process sigma level is 2. 99.73% adherence, process sigma level is 3. Right? So these values actually would help us to estimate the approximate sigma level given the process adherence to the customer specifications. Say if the process adherence to customer specifications is around about 85%, what can we say about the sigma level? So since 1 sigma level is 68.27% adherence and 2 sigma level is 95.45% adherence, so around about 85% adherence will be between 1 and 2 sigma level. Or it is 98% adherence. What can you tell about the process sigma level? So 2 sigma level is 95.45% adherence. 3 sigma level is 99.73% adherence. So 98% adherence will be between 2 and 3 sigma level. So we can make a rough estimate of the process sigma level if we know all these three values. So it's important for us to by heart these three values as a black belt. So you cannot just calculate and then come up with all these values. You need to know these values by heart, right? This is the only thing I'm asking you to by heart, right? So the area coverage within 1 sigma limit is 68.27%. Area coverage within 2 sigma limit, it is 95.45%. Area coverage within 3 sigma limits is 99.73%. And all these values are applicable only for normal distribution, not for any other continuous data distribution. We need to remember that. So that is why I specifically mentioned area coverage within various sigma limits for a normal distribution. So area coverage within 1 sigma limit is 6.6827 or 68.27%. And the explanation is if the process adherence to the customer specifications to the extent of 68.27% of the overall production, the process is said to be functioning at just 1 sigma level. So the non-conformance percentage or the defect percentage will be 31.73%. So let us look at a simple example to understand this. So for example, let us assume that the customer has provided the specification limits for the length of a product as 10 plus or minus 0.2 centimeters. So what does this indicate? So the target measure is 10 centimeters. The lowest specification limit is 9.8 centimeters, which is 10 minus 0.2 centimeters. And the upper specification limit is 10.2 centimeters, which is 10 plus 0.2 centimeters. So if only 68.27% of the total production has the length measuring between 9.8 and 10.2 centimeters, then the process is said to be functioning at just 1 sigma level. So which one would be considered as a conforming unit? Only if the length is going to measure anywhere between the LSL and the USL value. Then the customer would be willing to accept that unit as a conforming unit. So if only 68.27% of the overall production has a length measuring anywhere between the LSL and USL values, then the process is said to be functioning at just 1 sigma level, meaning 31.73% of the total production may have a length less than the LSL value or greater than the USL value. So all those units which are having a length outside the specification limits will be termed as non-conforming units or defects, right? So this is the explanation. Similarly, area coverage within 2 sigma limits 0.9545 or 95.45%. So if the process adherence to the customer specification is to the extent of 95.45% of the overall production, then the process is said to be functioning at 2 sigma level. So the non-conformance percentage will be 4.55%. Similarly, area coverage within 3 sigma limits will be 0.9973 or 99.73% if the process adherence to the customer specification is to the extent of 99.73% of the overall production. The process is said to be functioning at 3 sigma level. So at 3 sigma level, the non-conformance or the defect percentage will be 0.27%, right? So the final assessment, there can be a question wherein they will ask you to find out the area between plus 1.96 and minus 1.96. So let me also provide you the calculation so that you can pick the answer straight away from here. So how will you calculate area to the left of plus 1.96? So P of X less than or equal to plus 1.96. So what will be the rough estimate of this area? So within 2 sigma limits, we have the area as 95.45%, right? So here we have been asked to calculate within 1.96 sigma limits between plus 1.96 and minus 1.96. So it will be area less than 95.45%. So let us see. So first I will calculate the entire area to the left of plus 1.96. Apply the formula is equal to norm dot dust. X will be 1.96 comma mean is 0, standard deviation is 1, cumulative is 2. And then area to the left of minus 1.96 less than or equal to minus 1.96. Again is equal to norm dot test open bracket. We give the x reference value as minus 1.96 comma 0 comma 1 comma true. Right? So we need to subtract these two values in order to get the area between plus 1.96 and minus 1.96. So in terms of notation, this can be written as P of minus 1.96 less than or equal to X less than or equal to plus 1.96. We simply need to subtract these two values in order to get the answer. Right? So round this up to 4 decimals and we get the answer as 0.9500 or 95%. As I told you, it will be a value less than the 2 sigma limit value, which is 95.45%. So the area within 1.96 sigma limits is exactly 95%. Right? So there can be a question on this. So that's why I've given you this calculation. So you can straight away pick the answer from here. So area between plus 1.96 and minus 1.96 for a normal distribution will be exactly 95%. Fine. So we will go for a break now. So after we come back from the 15-minute break, we will look at how to calculate the actual sigma level given the process performance, right? So with all these values, we can make a rough estimate of the sigma level given the process adherence to the customer specification, right? But then how to calculate the actual sigma level given the process performance is something that we will see after a 15-minute break. And this calculation of sigma level is applicable only for normal distribution. So we cannot use this for non-normal distribution. So that's why I told you normal distribution is a very famous continuous data distribution. And we have good number of statistical tools and techniques which can be applied for analyzing a normally distributed data set, right? So after the break, we will see how to calculate the actual sigma level for a normal distribution. Hello friends, I'm back. Hope you're all back as well. So let us continue with the discussions regarding sigma level. Right, so we looked at the area coverage within various sigma limits for a normal distribution just before the break. So the area coverage within one sigma limit is 68.27%. Within two sigma limits, it's 95.45%, and within three sigma limits, it's 99.73%. So what is the meaning of all these values? We also understood about the same. So if the process adherence to the customer specification is to the extent of 68.27% of the overall production, then the process is said to be functioning at 1 sigma level. 95.45% adherence, 2 sigma level. 99.73% adherence, it will be 3 sigma level. But then we also need to understand how to calculate the actual sigma level given a process performance, right? So again, let me draw the bell curve. So we will keep it very simple. So we will not use some complex numbers here to perform the calculations. So we will assume this to be a standard normal distribution. So where the mean is 0 and standard deviation is 1. X bar is 0, small s is 1, right? And the lowest specification limit is given as -6. And the upper specification limit is +6, right? So we have been provided with mean and standard deviation along with the specification limits. So these matrices are enough for me to calculate the sigma level for a process performance, right? So sigma level is also a standardization formula. So that is why sigma level will also be denoted by capital Z, because sigma level is also a standardization formula. So it goes something like this. Again, no need to by heart these formulas. So Z is equal to minimum of mean minus LSL divided by the standard deviation, or USL minus mean divided by the standard deviation. So mean minus LSL divided by standard deviation, or USL minus mean divided by standard deviation, right? So minimum of these two values will be considered as the sigma level, right? But then if we find that the mean is aligning with the target, right? So when can we say that the mean is aligning with the target? So first and foremost, we need to calculate the target, right? So we need to find out what is the target given the two specification limits, the LSL and USL values. So LSL is -6, USL is +6. I've already told you that target will be the midpoint between LSL and USL. Or if you want to mathematically apply a formula to calculate the target, it will be USL plus LSL divided by 2. So that being the case, what will be the target for this scenario? So LSL is -6, USL is +6. So target will be 0, right? So target is 0. Mean is also assumed to be 0. So here is a scenario where the mean is actually aligning with the target. And remember, this is the first objective of Six Sigma, right? Align mean with the target. So LSL is -6, USL is +6 means the target is 0. So if the target is 0, target is the midpoint between these two specification limits. So if you want to mathematically calculate the target, then it will be 6 minus 6 divided by 2, which will be 0. So target is 0. Mean is also assumed to be 0 for this case. Then we can say that the mean is aligning with the target, which incidentally is the first objective of Six Sigma. That being the case, then we can call that process as a centered process. So mean is aligning with the target. We will call that process as a centered process. So in that case, there is no question of minimum of these two values. So we can either use the LSL side formula or the USL side formula and calculate the sigma level. The answer is going to be the same. Whether we apply the LSL side formula or the USL side formula, you'll get the same value. So that value can be treated as the sigma level. So the minimum doesn't arise at all if the mean is aligning with the target or the process is a centered process. So for this scenario, let me calculate the sigma level. So let me apply the LSSMC formula and calculate the sigma level. So for this scenario where the mean is found to be aligning with the target, I can use either the LSSMC formula or the USL formula to calculate the sigma level. So let me use the LSL formula to calculate the sigma level. So it is mean minus LSL. So 0 minus of minus 6, which will be plus 6 divided by 1, and the sigma level for this process performance is equal to 6. So even if you are going to apply the USL site formula, you'll get the same answer. So what is the USL site formula? USL minus mean. So 6 minus 0 divided by 1, which will be again 6. So whether we apply the LSL site formula or the USL site formula, we'll get the same answer as the sigma level, because the mean is aligning with the target. So the mean is aligning with the target. We can find out that the distance between mean and LSL is the same as the distance between mean and USL. So what is the distance between mean and LSL in terms of units? It will be 6 units. What will be the distance between mean and USL in terms of units? It will be again 6 units, right? So the distance between mean and LSL is the same as the distance between mean and USL, because the mean is aligning with the target, and target is the midpoint between LSL and USL, right? So if you dissect this sigma level formula, what we can actually find out is the standard deviation is in the denominator, right? Standard deviation is a metric which would actually help us to quantify the variation in the process performance, right? But then you find the standard deviation in the denominator in the Six Sigma or the sigma level formula, right? So the standard deviation is in the denominator. If you are able to reduce the standard deviation value, what will be the resultant output? So it's a pure mathematical logic. So if you are reducing the denominator value, you will see the resultant value increasing. So when we reduce the standard deviation value, we can increase the sigma level for a process, right? So this actually explains why the second objective of Six Sigma is relevant, reduce variation. So when I say reduce variation, we are looking at reducing the standard deviation value. The standard deviation value reduces, we can see an increase in the sigma level, right? So standard deviation and sigma level are contradicting matrices. Say, let us assume the standard deviation has got reduced to 0.5. Instead of 1, it has become 0.5. So what will be the resultant sigma level? It will be 6 divided by 0.5, it will be 12, right? On the other hand, we see an increase in the standard deviation value. So instead of 1, it has become 2. Now what will be the sigma level? It will be 6 divided by 2, which will be 3. Right? So decrease in standard deviation would result in increase in sigma level, or increase in standard deviation would result in decrease in sigma level. So standard deviation and sigma level are contradicting matrices, right? So I have introduced this manual formula just to make you understand the concept of sigma level, nothing else. So we are not going to use this formula anywhere, right? So even though for the manual calculation, you may use all these formulas, but then if you are using the Excel template, then there is no need for us to apply any of these formulas there. Fine. So standard deviation and sigma level are contradicting matrices, number one. And number two, what exactly is sigma level? If you see here, what exactly is a sigma level? So conceptually speaking, sigma level is nothing but the number of standard deviations you are able to pack between mean and LSL, or between mean and USL, whichever is minimum. So the minimum doesn't arise if mean is aligning with the target, as I just now mentioned. Now, what is the standard deviation value? It is 1 unit. So what is the distance between mean and LSL? 6 units. So how many standard deviations you'll be able to pack between mean and LSL? 6 standard deviation. So that is why the sigma level is 6. Similarly, what is the distance between mean and USL? The same 6 units. So how many standard deviations you'll be able to pack between mean and USL? The same 6 standard deviations. So that is why even when we apply the USL side formula, the sigma level will be 6. Clear how to calculate the sigma level? So another thing that we need to clearly remember here is when it is nominal, the better kind of metric. So only if it is nominal, the better. We will have both USL and LSL provided to us, right? So the nominal, the better kind of metric, both LSL and USL will be applicable for that scenario. So for nominal, the better, the mean will provide its best performance only when it is aligning with the target, right? So the mean will provide its best performance only when it is aligning with the target. So the mean is going to move away from the target, then the performance is likely to deteriorate, right? So the mean can move either on the left hand side or on the right hand side, but the performance will slowly deteriorate. So the mean can provide its best performance only when it is actually aligning with the target. So take the example of blood pressure. So what is the target measure? 120/80. So when can a person give his best performance as far as health is concerned? Only when the blood pressure reading is aligning with the target, which is 120/80. So if it is going to deviate on either side, right, the upper side or on the lower side, then the person will be called as a blood pressure patient, correct? So if it is on the upper side, high blood pressure, but in the lower side, low blood pressure. So when can, you know, uh, the blood pressure measure can provide its best performance? Only when it is aligning with the target, which is 120/80. So for all these nominal, the better kind of matrices, the mean will give its best performance only when it is aligning with the target. So if it is going to deviate from the target, obviously we will see a deterioration in the performance, and that would be reflecting in the sigma level. So the sigma level is not going to be the same as it was when mean was aligning with the target. So the mean is going to move away from the target, either on the LSL side or on the USL side. You will see a dip in the sigma level, right? So as per Motorola, what they said was, in the long run, the mean will not remain in the same position as it was during the short run. The mean will shift and drift 1.5 either to its left or to its right. So as per Motorola, the mean in the long run will not remain in the same place as it was during the short run. The mean will shift and drift 1.5 either to its left or to its right. So let us assume that the mean is actually shifting towards the USL side. So instead of 0, the new mean will become 1.5 plus 1.5, correct? So let us assume that the mean is actually shifting towards the USL side. So as per Motorola, in the long run, the mean will shift and drift 1.5 either to its left or to its right. So we are assuming that the mean is shifting towards the right hand side. So the new mean will become 1.5. So it is a 1.5 shift, right? But then Motorola doesn't say anything about the standard deviation, right? So they assume that the standard deviation will remain the same in the long run. Only the mean will actually shift 1.5 either to its left or to its right. So how come it is exactly equal to 1.5? Why it cannot be 2.5 in the long run? There is no answer. So how come standard deviation remains the same? No answer, right? And there is no other counter alternative for this Motorola theory. So Motorola is the one which actually introduced the Six Sigma methodology. So for this long-term sigma level calculation, there is no other counter alternative for this Motorola theory, and we still accept the Motorola logic in order to derive the relationship between the short-term sigma level and long-term sigma level. So this particular logic may actually hold good for a manufacturing scenario where we would be dealing extensively with machineries. So machineries in the long run will obviously depreciate and the performance will not be the same as it was during the short run. But then if you are looking at a human intensive process like a service process. So as the employees gain more expertise, more experience working in that process, so they will also gain more proficiency in that process and will start committing lesser number of errors. So as they spend more time working that process, the employee's performance is likely to improve. So it'd be exactly the opposite, right? But as I told you, since there is no other counter alternative for this Motorola theory, we still accept the same to derive the relationship between the short term and the long term sigma level. Now, assuming that the mean has shifted towards the USL side and the new mean is 1.5. So what will be the new sigma level? So this will be your long-term sigma level, right? The earlier one that we derived was the short-term sigma level. So what will be the long-term sigma level? So since the mean is tilting towards the USL side, so we need to apply the USL side formula to calculate the sigma level. So what is the USL side formula? Because the distance between the new mean and the USL is going to be less compared to the distance between the new mean and the LSL. So here we are considering the minimum of these two as the sigma level. So since the distance between mean and USL is going to be much lesser compared to the distance between mean and LSL, we will consider the USL side formula to calculate the sigma level, right? So even otherwise, you can just remember like this. So if the mean is not aligning with the target, we need to find out to which side the mean is actually tilting towards. So keeping the target as the reference point, we can easily find out to which side the mean is actually tilting towards. So the mean is tilting towards the USL side. We need to apply the USL side formula to calculate the sigma level. Or if the mean is tilting towards the LSL side, we need to apply the LSL side formula to calculate the sigma level. Or if you want to be safe, we can apply the full formula in Excel, that is equal to minimum of provide all the values. So the Excel will identify which one has the minimum value and it will actually throw that as the sigma level. But then we know since the mean is tilting towards the USL side, let us apply the USL side formula to calculate the new sigma level, which is the long-term sigma level as per Motorola. So what is USL? It remains as plus 6 minus mean is 1.5 divided by standard deviation, which is 1. So the new sigma level or the long-term sigma level will be 4.5. So the short-term sigma level is 6. The long-term sigma level will be 1.5 less than the short-term sigma level as per Motorola. If the short-term sigma level itself is 4.5, then the long-term sigma level will be 3. If the short-term sigma level itself is 3, then the long-term sigma level will be 1.5. So this is the relationship between the long-term and the short-term sigma levels as per Motorola, right? So we need to remember the relationship between the long-term and short-term sigma level, even though we are not going to apply this anywhere in our exercises. But then we need to remember that this is the relationship. So even the assessment, if they provide you with the notation ZST, we need to understand that it is short-term sigma level. So ZLT will be long-term sigma level. So let us quickly look at the summary and then recap what all we discussed with regard to calculation of sigma level. Right. So as I told you, the mean is aligning with the target. We will call that process as centered process. So for a centered process, the distance between mean and LSL will be the same as the distance between mean and USL. And hence, we can apply either the LSL side or the USL side formula to calculate the sigma level. And then conceptually speaking, what exactly is sigma level? So sigma level is the number of standard deviations we are able to pack between mean and LSL or between mean and USL, whichever is minimum. So the minimum will not arise if the mean is aligning with the target. And then the sigma level and standard deviation are contradicting matrices. If we reduce the standard deviation, which is the second objective of Six Sigma, we will be able to increase the sigma level and vice versa. So I told you, the best position for mean is to align with the target. So that is the position where the mean will give its best performance, right? So if it is going to move away from the target, as we saw in this long-term sigma level calculation, when mean is going to move away from the target, so we see a reduction in the sigma level because the process performance is bound to deteriorate. So even if the mean is going to move towards the LSL side, so we would have applied the LSL side formula to calculate the sigma level. So you would have got the same 4.5. Just assume the mean to be minus 1.5, right? So applying the LSL side formula, so what will be the sigma level? Mean is minus 1.5. And LSL is minus 6. So minus 1.5 minus of minus 6. So minus 1.5 plus 6 divided by standard deviation, which is 1. So again, 6 minus 1.5, you would have got 4.5 as the sigma level, right? So mean are tilted towards the LSL side. Still 4.5 would have been the sigma level. So whether the mean is tilting towards the LSL side or USL side, if it is going to move away from the target, then we can see a deterioration in the process performance and a reduction in the sigma level, right? So that's why I told you, mean aligning with the target is the best position of or the best position for mean where it can actually provide its best performance. And that is the first objective of Six Sigma. So we will be able to improve the sigma level by having the mean align with the target. But if you further want to improve the sigma level, then we need to look at fulfilling the second objective of Six Sigma, which is reduce variation, right? So that is what is written here. So if you reduce the standard deviation value, which is the second objective of Six Sigma, we will be able to increase the sigma level and vice versa. Vice versa means if we happen to see the standard deviation increasing, then it would result in reduction in the sigma level. So the others, logic also will hold good. That is why we say vice versa. And then the relationship between the long-term and the short-term sigma levels, right, as per Motorola. So the short-term sigma level will be long-term sigma level plus 1.5 or the long-term sigma level will be short-term sigma level minus 1.5, right? So let us look at couple of exercises under normal distribution and then we will move to the next section. So the same sheet, right below all these explanations and calculations. So I have provided you with the exercises for normal distribution and you will not get any exercise pertaining to binomial or Poisson distribution in the final assessment, but you will get multiple questions relating to normal distribution exercises, right? So please pay attention. So let us look at exercise number 1. So it says the length of a unit product is normally distributed with mean 32.3 centimeters and standard deviation 0.2 centimeters. So I had mentioned this very clearly. For a normal distribution, the historical performance will be given in terms of mean and standard deviation because these two are the primary matrices for a normal distribution. And we are talking about length of a unit product. So length is nominal, the better kind of metric. So both USL and LSL will be applicable for this scenario, right? So if you look at the second part of the question, it says very clearly that if the customer specifications range from 32 to 33 centimeters, estimate the yield percentage. So this is the question asked. So even though we have been asked to estimate only the yield percentage, we will also go ahead and calculate the sigma level for this process performance. But then we need to understand this case scenario by drawing the distribution diagram. So as I told you, whenever we have a case scenario, it is always better to draw the diagram to get a better understanding about the case scenario. So since the data is normally distributed, we will draw the bell curve, right? And what is the mean given in the problems? So please bear with my drawing. So mean is 32.3 centimeters, right? and standard deviation is 0.2. And we have the LSL as 32 and USL as 33. So if LSL is 32 and USL is 33, what will be the target? LSL is 32, USL is 33, what will be the target?
Target will be mean.
No. Target is totally different from mean. Mean can align with the target, but target is an independent value. It has got nothing to do with mean. So it all depends on the specification limit. So LSL is 32, USL is 33. I told you, target will be the midpoint between LSL and USL. Should never forget this. So target will be the midpoint between LSL and USL. So what will be the target for this scenario?
LSL plus USL
32.5.
32.5. Don't even need to apply the formula. So LSL is 32, USL is 33. So the target will be 32.5. So it will be somewhere here, 32.5, correct? To the right hand side of mean. 32.5 as the target will lie on the right hand side to this mean value, which is 32.3. Now, keeping the target as the reference point, to which side the mean is actually tilting towards, the USL side or the LSL side? So target is 32.5, mean is 32.3. To which side the mean is actually tilting towards? So one thing that we can understand is mean is not aligning with the target, right? So target is 32.5, mean is 32.3 as given in the problem. So mean is not aligning with the target. But then which side the mean is actually tilting towards? So we need to keep the target as the reference point and find out, right?
It's the left side, LSL.
LSL, right? So target is to the right hand side of the mean. So that being the case, the mean is actually tilting towards the LSL side. So you can also calculate what is the distance between mean and LSL and mean and USL. So whichever side the distance is less, so we can say that the mean is tilting towards that side. So here the distance between mean and LSL will be definitely less than the distance between mean and USL. So we can say that the mean is actually tilting towards the LSL side. So when we calculate the sigma level, so we need to apply the LSL side formula to calculate the sigma level. So that is why, we are kind of making an observation like this. But then if you want to calculate the yield percentage, then which area in this process diagram we need to shade or we need to find out. So which area in this process diagram we need to estimate in order to come up with the yield percentage. So what will be the yield? So how will you calculate yield? When the unit product is going to adhere to the customer specifications, right? So that will be taken into consideration for calculation of yield. So yield or accuracy percentage all mean one and the same, right? So the defect percentage will be the ones which are falling outside the specification limits. So for calculating the yield percentage, which area in this process diagram I am supposed to shade? So anything between LSL and USL, the customer is going to accept it as conforming unit. And the conforming unit is going to be considered for calculation of the yield percentage. So that being the case, which area in this diagram I need to shade for calculating the yield percentage? Tell me.
Between 32.3 to 32.5.
Why 32.5?
Between 32 and 33.
Because that is the mid of between 32 and 33.
No, this is the target. No, that is the target. But then, when will the customer accept a unit product as a conforming unit? When it is going to fall anywhere between the measurement value is going to fall anywhere between 32 and 33.
Yeah,
Okay.
complete
So the
area.
complete
Yeah,
area
right.
between 32 and 33 is what we need to find out for calculating the yield percentage. Clear? So once you draw the process diagram, it becomes very clear for you as to what exactly you need to estimate or what exactly you need to calculate, right?
Yeah.
So,
Right.
so the area between 32 and 33 is what we will consider for calculation of the yield percentage. Now let me just summarize all these values and then we will perform the calculation. So this is similar to the area within the sigma limits calculation, right? So the same kind of logic needs to be applied. So what I can do in order to find out the area between 32 and 33, first and foremost, I will find out the entire area to the left of 33, right? And we'll get the area extending beyond 32 as well. From that, if I'm going to subtract the area to the left of 32, I'll be getting the area between 32 and 33. So the same logic will be applied here as well for calculating the yield percentage. So let me kind of summarize all these input values and then we will perform the calculations. So USL value is 33 and the LSL value is 32. So we can understand that the target is 32.5. So mean is 32.3. So we can understand that the mean is not aligning with the target and is actually tilting towards the LSL side. So whatever information we can gather, we need to summarize all those things. And then the standard deviation is given as 0.2, right? Now, as I told you, first we need to find out the entire area to the left of 33. So I will use the probability notation P of x less than or equal to 33. So you'll get the entire area to the left of 33. So what is the Excel formula is equal to norm.dist open bracket. So x will be the USL value, which is 33, comma, mean is 32.3, comma, standard deviation is 0.2, comma, cumulative, as I told you, it will be always true, right? Because you'll be dealing mostly with less than or equal to scenarios for a continuous data probability distribution. So cumulative will be true for this. Get the entire area to the left of 33. So from this, we need to subtract the area to the left of 32, which is the LSL value. Again, applying the formula is equal to norm.dist. LSL value is 32, comma, mean is 32.3, comma, standard deviation is 0.2, comma, cumulative will be true, right? Now I can find the area between 32 and 33. So P of 32 less than or equal to x less than or equal to 33. So this would indicate that we are calculating the area between 32 and 33. Just subtract these two values. So you'll get the yield rate and round this off to 4 decimal places. So the yield rate is 93.3%. So the yield percentage. So this is the area between USL and LSL values, right? So anywhere between USL and LSL, the customer is going to accept the unit product as a conforming unit. So the conforming unit is the one which will be considered for calculation of the yield percentage. So the area between 32 and 33 would actually represent the yield rate, and that yield rate can always be expressed in terms of a percentage value, so that it will become yield percentage. So this will be 93.30%. And what will be the rough estimate of sigma level? So it is likely to be between 1 and 2, right? 1 sigma level is 68.27%. 2 sigma level, the adherence is 95.45%. 93.3% could be between 1 and 2 sigma level. So let me find out the actual sigma level. even though it is not asked in the question, but still let us go ahead and find out. So as I told you, since mean is aligning or tilting towards the LSL side, so we need to apply the LSL side formula to calculate the sigma level. So what is the LSL side formula? It is mean minus LSL divided by the standard deviation. So the sigma level is 1.5. Right? So the actual sigma level is 1.5 for this case scenario. So if you want to calculate this using Minitab, so we need to find out the area to the left of 33 and also the area to the left of 32, and then come back to Excel and then subtract these two values to get the yield rate. And of course, sigma level cannot be calculated using Minitab, so we need to depend on the manual formula in Excel to perform the calculations. So let me go to Minitab. So we click on Calc, Probability Distributions. Under that, we have Normal. Let's click on Normal. So we can have cumulative probability. So mean is 32.3 and standard deviation is 0.2. Choose input constant. So the input constant, first we will find out the entire left-hand side area to the value 33. So give the input constant as 33. So get the left-hand side area as 0.999767. And that is exactly what we also got using the Excel formula. And now the area to the left of 32. So again go to Calc, Probability Distributions, Normal, and input constant will be 32. So the left-hand side area is 0.0668072. 0.0668072. So subtract these two values, you will get the area between 32 and 33, and that will be considered as the yield rate. So this in terms of percentage will be 93.3%, which will be the yield percentage, and in terms of sigma level, so this will be 1.5 sigma level. Fine. So let us also see how to use our template to perform the calculations. So this is very, very important because as I told you, so you may get multiple questions pertaining to normal distribution in the final assessment. So you need to know how to use this template. So this is the normal distribution template. Just provide the input values. That's it. So what is the sample mean? It is 32.3 centimeters. Sample standard deviation, 0.2 centimeters. What is LSL? 32. What is USL? 33. So having provided all the input values, please do not forget to choose the right option. So since it is nominal the better kind of metric, and we have been provided with both LSL and USL, we need to choose the right option, both LSL and USL from this drop down, right? So for higher the better kind of metric, we all know only LSL will be applicable, right? So you need to leave the USL field blank and then choose the option only LSL. And similarly for lower the better, only USL will be applicable. So in that case, LSL wouldn't have been provided to you. So we need to leave the LSL field blank and then provide the value for USL. And here in the drop down, we need to choose the option only USL. But when it is nominal the better, we will have both LSL and USL applicable for that scenario. And after providing the values for both LSL and USL in the input section, please do not forget to choose the option both LSL and USL, the next field. Only after that you'll get the correct answer, right? So we need to choose this option. This is very, very important. So conformance to customer specifications is what we would call as the yield rate. And the non-conformance to the customer specifications is what we would call as the defect rate. And this can always be converted and expressed in terms of a percentage value. So 0.9330 will be 93.3%. So let us not worry about these two matrices, CP and CPK as of now. So we will learn about these matrices when we cover process capability analysis tomorrow, right? So for now, just look at the sigma level. So sigma level is 1.5 for this scenario. Now, as I have told you that the best position for mean is to align with the target. So that is the first objective of Six Sigma as well, right? So the best position for mean when we are dealing with nominal, the better kind of metric, is for the mean to align with the target. So that is where the mean can actually provide its best performance. Always think about that blood pressure metric, right? So the target value will be 120/80. So only if the average measurement value is 120/80, the person will be considered to be healthy, right? So even if it is going to deviate from that, target value of 120/80, either on the left hand side or on the right hand side, you can see the performance deteriorating. So in the same way, even for any other measurement dimension metric, which would fall under nominal, the better kind of category, the best position for mean is to align with the target. That is where mean can actually provide its best performance. If the mean is going to move away from the target, either on the left hand side or on the right hand side, the performance will obviously deteriorate, and that would be reflecting in the sigma level value as well, right? So now what I'm going to do, I'm going to make an assumption that the first objective of Six Sigma has been fulfilled, right? And the mean is now aligning with the target. So the new mean will also be 32.5 like target, and with mean being 32.5, let us recalculate the yield percentage and also the related sigma level and see what kind of improvement we will be able to see, right? So, and see what kind of improvement we'll be able to witness. So here, we are making a small adjustment. What is adjustment? We are moving mean from 32.3 to 32.5 and making it align with the target. With a small adjustment, we can see how much the yield percentage is going to improve and how much the sigma level is also going to improve. So let us make that assumption. So let us assume that the first objective of Six Sigma has been fulfilled and the mean is now aligning with the target. So with this improvement made, let us calculate the improved yield percentage and the improved sigma level. Let us see how far we are able to improve the yield percentage and by how much the sigma level has also increased. So let us perform the calculations. So we will summarize all these values. Only thing is we will consider the mean to be 32.5. So the new mean will be 32.5. Right? It's now aligning with the target. So first let me calculate the entire area to the left of 33. So this will be is equal to norm dot test open bracket. So the USL value, comma, mean 32.5, comma, standard deviation, comma, cumulative is true. And then the area to the left of 32, P of x less than or equal to 32. Again, norm dot test open bracket. So 32, comma, 32.5, comma, 0.2, comma, cumulative will be true. Right? Now we can find out the area between 32 and 33. So P of 32 less than or equal to x less than or equal to 33. So you just need to subtract these two values. That's it. this minus this, and we need to round this off to 4 decimals. So you get the answer 0.9876. So the yield percentage has improved to 98.76%. Right? So it was earlier 93.3%. So what is the adjustment that you made here? So we simply moved the mean from 32.3 to 32.5 and made it align with the target. That's it. So we just moved the mean from 32.3 to 32.5, made it align with the target. The small adjustment made, you can see a drastic improvement in the yield percentage. And the yield percentage has gone up from 93.3% to 98.76%. And what will be the sigma level for this particular performance? So since mean is assumed to be aligning with the target, we can use either the LSL side formula or the USL side formula to calculate the sigma level. So for a change, let me use the USL side formula to calculate the sigma level. So it will be USL minus mean divided by the standard deviation. So the sigma level has also improved from 1.5 to 2.5. So this is the kind of improvement we'll be able to witness when mean is actually aligning with the target for nominal the better kind of metric. So we can see a drastic improvement in the yield percentage from 93.3% to 98.76%. The sigma level has also improved from 1.5 to 2.5. The sigma level has also improved from 1.5 to 2.5. So this actually proves our theory that when mean is aligning with the target, obviously there will be an improvement in the yield percentage and also the sigma level of the process. Right? So if you want to further improve the sigma level, what is that we are supposed to do? So the first objective of Six Sigma has been fulfilled. That is aligning mean with the target. And that is the best position for mean as well. We have already seen that, right? Now, 2.5 as sigma level is not enough for me. So I want to improve the sigma level further. What is that I'm supposed to do?
Standard deviation, reduce.
Very good. Very good. So we need to fulfill the second objective of Six Sigma, which is reduce variation. So only by reducing the standard deviation value, we will be able to further improve this sigma level. So we'll play around with this template. So let me just make that adjustment. So the sample mean, the new mean is 32.5. Moment you change this to 32.5, you can see the yield rate and the sigma level automatically changing in the output section. So the yield rate has become 0.9876 and sigma level has become 2.5. But if you further want to improve the sigma level beyond this 2.5 mark, then we need to look at reducing the variation, which is the second objective of Six Sigma. There is nothing but reducing the standard deviation value. So let me assume the standard deviation has been reduced from 0.2 to 0.15, right? You can see the sigma level improving to 3.33, right? So this is exactly what I'm supposed to do as part of my Six Sigma project. So having aligned mean with the target, which is like fulfilling the first objective of Six Sigma, we need to look at reducing the variation. This is the second objective of Six Sigma in order to improve the sigma level further. So let me just revert back to the old standard deviation value. Fine. So this is as far as exercise number 1 is concerned. So if you are provided with nominal the better kind of metric and you'll be asked to calculate the sigma level or the yield percentage, in that case, you will have the sample mean and the sample standard deviation provided as input values. along with both LSL and USL, right? For nominal the better, you'll be provided with both LSL and USL. So you can use this template, provide all the input values and calculate either the yield percentage or the defect percentage or the sigma. Fine. So let us look at exercise number 2. So this is, slightly different from the exercise that we just now solved, which is exercise number 1. So it says revenue in dollars is normally distributed. So revenue as a metric, what is the type? What is the metric type? Revenue as a metric would fall under which category? Is it nominal the better or higher the better or lower the better?
Revenue will be higher the better.
Higher the better, right? Revenue, sales, profit, all these are higher the better kind of matrices, right? So that being the case, only LSL will be applicable for this scenario. Higher the better means we will not have both LSL and USL provided to us. Only LSL will be applicable for this scenario. So the exercise says that the revenue in dollars is normally distributed with a mean of $15,250 per month and standard deviation of $150. So if the minimum revenue target per month is $15,000, calculate the probability of meeting the minimum revenue target. So I told you, for higher the better, you'll always be provided with some minimum targets. So that minimum target is what we need to consider as the lower specification limit. So here again, the minimum revenue target that is given as $15,000 is to be considered as LSL for this exercise. So as we did for the previous exercise, let me draw the distribution diagram and try to find out which area we are supposed to calculate in order to estimate the probability of meeting the minimum revenue target. So revenue is normally distributed. So I draw a bell curve. Now what is the mean? Mean is 15,250 and the standard deviation is 150. And what is the minimum revenue target? It is 15,000. And I told you that minimum revenue target is what we need to consider as the lowest specification limit. Now, if you want to estimate the probability of meeting the minimum revenue target, then which area in this process diagram we are supposed to find out? So if you want to calculate the probability of meeting the minimum revenue target of $15,000, which area in this process diagram we are supposed to calculate?
Left to the 15,000.
Left to the 15,000 means we'll fall short of meeting that target, right? So if you're achieving only 14,250, that means you are falling short of the revenue target, meeting the minimum revenue target. So when can you say that you have met the minimum revenue target? So when can you say that you have achieved 15,000? So when it is
Exactly.
15,000 and above, correct?
Yeah, right.
15,000 and above. So which area we need to find out?
Right
In
side.
the right side of 15,000. Clear? Others? So when 15,000 is the minimum revenue target, so the probability of meeting the minimum revenue target will be the area to the right hand side of this value 15,000. So 15,000, and if you go towards the right hand side, it will be greater than 15,000. So 15,000 and above is when you can say that you have met the minimum revenue target. So the right hand side area to this value 15,000 is what we are supposed to find out in this particular or for this particular case scenario, right? So the minimum revenue target is to be treated as, or since revenue is higher the better type of metric, so the minimum revenue target is to be considered as LSL. And for higher, the better type of metric, only LSL will be applicable. So for higher, the better kind of metric, only LSL will be applicable. Right? So we need to estimate the probability of meeting the minimum revenue target of $15,000. And hence, we need to calculate the area to the right of 15,000. Here. So this is like at least 15,000. So in terms of notation, this will be P of X greater than or equal to 15,000. So this is what we are supposed to find out. But then we know Excel and Minitab can provide the probability values only for equal to and less than or equal to. So it cannot provide the probability value for greater than or equal to scenario. So this has to be converted in terms of less than or equal to. And this is a continuous data. So for discrete data, we have already derived this notation. What is that? So for converting greater than or equal to into less than or equal to, so P of X greater than or equal to R can be rewritten as 1 minus P of X less than or equal to R minus 1. One number less than the original value, because discrete values cannot take decimals. So they will jump only in terms of whole numbers. So it can either be 20 or 19. So it cannot be a value in between 20 or 19. So that is why it was R minus 1, right? When we converted greater than or equal to into less than or equal to. But here we are talking about continuous data, which can also take decimal values. So 14,999 and 15,000 in between, we can have lot of decimal values, right? So it can also take those decimal values. So the P of X greater than or equal to 15,000 will be rewritten as 1 minus P of X less than or equal to 15,000. Because we are dealing with continuous data. So one number less than the original value will hold good only for discrete data probability distribution. For continuous data, since the continuous data can also take decimal values, so P of X greater than or equal to R will be rewritten as 1 minus P of X less than or equal to R. That's it, right? We don't have to subtract one number less than the original value in case of continuous data conversion. Now we can find out 1 minus P of X less than or equal to 15,000. So this will be 1 minus norm dot test open bracket. So 15,000 is the X value. Mean is 15,250. Standard deviation is 150 and cumulative will be true. And we need to round this off to 4 decimal places and provide the inference. So what will be the inference for this? The inference will be there are 95.22% chances of meeting the minimum revenue target of $15,000. Right? So what will be the sigma level for this scenario? So this is a one-sided specification limit exercise. So since the metric is not nominal, the better. So we will not be provided with both LSL and USL values. So the metric is higher, the better. So only LSL will be applicable. So for calculation of sigma level, we will apply only the LSL side formula, because USL side formula will not be applicable at all, because USL is not applicable for higher the better kind of metric. Only LSL will be applicable. So we need to use the LSL side formula to calculate the sigma level. So what is the LSL side formula? It is mean
minus
15,250 minus LSL 15,000 divided by the standard deviation, just 1. So it will be 1.67. So sigma level for this will be 1.67. Right? So if you are using Minitab to perform the calculations, you need to first find out P of X less than or equal to 15,000, and then we need to subtract that value from 1. So we go to calc and then probability distributions, then choose normal, and the mean here is 15,250 and the standard deviation is 150 and the input constant will be 15,000 and we click on OK. So you get the value 0.0477904. So 0.0477. So this will be 1 minus 0.0477. Will give you 0.9522 or 95. Right? So 95.22% chances of meeting the minimum revenue target of 15,000. So a similar kind of exercise can come as a question in the final assessment. So instead of revenue, they would have given sales as the metric. So instead of revenue, they would have given sales as the metric and the values could be different, but the format is going to be the same. So they would have asked you to calculate the probability of meeting the minimum sales target in that case, right? So instead of revenue, they would have given sales. So sales is also higher the better kind of metric. And they would have also provided you with the minimum sales target. So which would be a continuous value. And you'll be asked to estimate the probability of meeting the minimum sales target. And you need to follow the same logic, right? So this is the calculation logic. But then in the final assessment, you can always make use of this template. Just provide all the input values here. So what is the sample mean? 15,250. What is the sample standard deviation? 150. What is the LSL value? 15,000. What is the USL value? It is not applicable. So when it is not applicable, leave it blank. You don't have to really enter anything here. But please do not forget to choose only LSL. Since only LSL is applicable, from the drop down, we need to choose only LSL. That's it. So you will see the conformance to customer specifications, which is the yield rate, and it is 0.9522. So 95.22% is the probability of meeting the minimum revenue target of $15,000. And the sigma level is 1.67. That is exactly what we also got. Right? So you can get, a similar kind of a problem in the final assessment. So both exercise number 1 and exercise number 2 under normal distribution, you can get problems the same format, the final assessments as well, right? In fact, exercise number 1 can get multiple problems like that in the final assessment, not just one single problem. You can get multiple exercises pertaining to exercise number 1 in the final assessments, both in the green belt as well as the black belt final assessment. Right? So you can always make use of the template. So in case you have some confusion with regard to identifying the right template, you don't have to worry because I have given the template reference sheet at the end of this file. So the final sheet in this exercise file is the template reference table, right? So this would actually help you to identify the right template for a given scenario. Say if it is like a descriptive statistics calculation and you are provided with some data set and you are asked to calculate either the IQR value or the Q0 and Q4 values, the outlier limit on the lower side or the outlier limit on the upper side. So we need to use this template that is given here. But then I also provided you with the link, so you just need to click on this and it will take you to the place where the template is placed, right? So it will take you to the area where the template is placed. So you just need to provide the input values and get the answer. That's it, right? Similarly, if you look at the second one, only thing is scrolling through all these sheets is going to consume some time. So the second one is the roll throughput yield calculation. So you would have been provided with the throughput yield values in percentage. So as I told you, we need to convert them in terms of decimals, and you can use the template under exercise number 2 in the sheet run chart and RTY in order to calculate the RTY percentage. Right? And then the third one, it's a normal distribution. The problems that we solved just now. So you will be provided with mean, standard deviation, and specification limits. Nominal the better, you'll be provided with both LSL and USL. If it is going to be higher the better, you'll be provided only with LSL. So in that case, you'll be asked to calculate either the sigma level or the yield percentage or the defect percentage. So we need to use the template given in the normal sheet. Just click on this. It will take you to the template which we used just now for performing all these calculations pertaining to normal distribution exercises. Clear? So this is what it is. So today we looked at the probability distribution exercises. So binomial distribution, so which will be part of the discrete data probability distribution. So binary discrete data would follow binomial distribution, and proportion is the primary metric for representing binomial distribution. And in the binomial distribution exercises, the historical performance will be given in terms of the proportion of a binary discrete event, and we'll also be provided with the sample size. This is very, very important, right? Because sample size will be in the denominator if you want to calculate the proportion value. So sample size is a very important input value as far as binomial distribution is concerned. And then we looked at Poisson distribution, which is the count discrete data would actually follow Poisson distribution, and the primary metric will be average, denoted by lambda. And in case of Poisson distribution, will be provided with the historical average, and you will not find sample size because that will be irrelevant for a Poisson distribution exercise. So you'll not be using the sample size for Poisson distribution exercise. Just the historical average is enough, and will be provided with the value for which you'll be asked to estimate the probability. That's it, right? So we saw how to calculate the binomial distribution and Poisson distribution problems. And then we moved on to normal distribution. And a normal distribution we understood will be represented by a symmetric bell curve. And the primary matrices are mean and standard deviation. And then we looked at a very important concept called standard normal distribution. So for a standard normal distribution, the mean will always be equal to 0 and the standard deviation will always be equal to 1. And we looked at the area coverage within the various sigma limits for a normal distribution. Within 1 sigma limit, 68.27%. Within 2 sigma limits, 95.45%. Within 3 sigma limits, 99.73%. And we also understood what these values would actually indicate. And then we also saw how to calculate the actual sigma level for a normally distributed scenario. So sigma level can be calculated by applying the standardization formula minimum of mean minus LSL divided by standard deviation, or USL minus mean divided by standard deviation. But then if mean is aligning with the target, then we call that process a centered process. Then in that case, the distance between mean and LSL will be the same as the distance between mean and USL. And we can use either the LSL side formula or the USL side formula to calculate the sigma level. But if mean is not aligning with the target, we need to find out to which side the mean is actually tilting towards. So keeping target as the reference point, so target will be the midpoint between LSL and USL, for nominal the better kind of metric. So we need to find out whether the mean is tilting towards the LSL side or the USL side. If it is tilting towards the LSL side, we need to apply the LSL side formula to calculate the sigma level. If it is tilting towards the USL side, we need to apply the USL side formula to calculate the sigma level. So sigma level conceptually is nothing but the number of standard deviations we are able to pack between mean and LSL or mean and USL, whichever is minimum. So minimum will not arise if mean is aligning with the target or if the process is a centered process. And again, standard deviation and sigma level are contradicting matrices. By reducing the standard deviation, which is reducing the variation, we will be able to increase the sigma level. And we also worked out a couple of exercises under normal distribution. So tomorrow we look at how to perform the normality test, and if the data distribution turns out to be non-normal, then how to convert that non-normal distribution into a normal distribution. And then finally, the measure phase, we'll be looking at a concept called process capability analysis for both discrete and continuous. So with that, we would close the measure phase, and then we'll proceed to the analyze phase, which is the third phase in the DMAIC approach, right? So we will close the sessions for the day, and we will continue with our discussions tomorrow as well. So we'll be looking at the normality test first thing tomorrow. Right? So good night. Thanks for your time today. We'll connect at the same time tomorrow evening.
Thank you.
Thank you.